The universe, a realm of unimaginable scale and mystery, may hold within it dark and terrifying entities whose existence challenges everything we know. Hidden in the vastness of space, black holes, silent giants of the cosmos, loom like monstrous voids that devour stars, entire galaxies, and perhaps even the very fabric of space-time itself. These colossal structures are not mere curiosities, but fundamental forces that shape the universe's deepest secrets. In this journey, we venture into the depths of the cosmos, uncovering the eerie and enigmatic presence of the most formidable black holes ever discovered. Among them is the mind-boggling titan known as Taun 16, a celestial beast whose mass defies comprehension. As we delve deeper, we will confront the dark mysteries surrounding the ominous black hole located in the center of OJ 287, a binary system of black holes that seems almost alive with its rhythmic eruptions. We will also explore the lurking terror in the heart of our very own galaxy, Sagittarius A, a black hole whose presence keeps even the stars at bay. Finally, we will explore the relentless appetite of M87's supermassive black hole, a cosmic vacuum that consumes everything in its path. Taun 618, a titan among titans, stands as one of the largest black holes known to humanity. Its sheer scale is nothing short of terrifying. Imagine a mass millions of times heavier than our sun, compressed into a point so dense that even light cannot escape its gravitational grip. Taun 618's mass exceeds 66 billion times that of our sun, a mind-boggling number that reveals the immense power it wields. Its gravitational pull is so strong that it draws everything within its reach, gas, dust, and even entire stars, into its dark embrace. This black hole is not just a passive entity, it is an active, hungry beast that emits intense radiation as matter spirals inward. This radiant energy is so powerful it can outshine entire galaxies, earning Taun 618 the designation of a quasar, an ultra-bright cosmic object powered by the accretion of material into a black hole. But it's not just its size that makes Taun 618 so horrifying. The very act of consuming material creates an extraordinary spectacle, transforming it into a cosmic vacuum. As the black hole pulls in everything around it, space itself is warped, and time, as we know it, bends. The immense distance between Earth and Taun 618, billions of light years, only heightens the sense of scale. Yet, as daunting as it may seem, studying Taun 618 is vital for our understanding of black hole formation and evolution. It forces us to confront the possibility that there may be many more such behemoths lurking in the vast expanse of the universe, awaiting discovery. To put the scale of Taun 618 into perspective, consider this. Its mass is nearly 30 billion times that of our sun. That staggering figure means that Taun 618 is not just a black hole, but a gravitational force of nature capable of shaping the very structure of its surrounding space. The combined mass of the entire Milky Way galaxy, including its stars, gas, and dark matter, is somewhere between 100 and 200 billion times the mass of the sun. Thus, Taun 618 represents a significant fraction of that mass, and if it were located in our cosmic neighborhood, its gravitational pull would be felt across vast distances. It would warp the motion of nearby stars and cosmic objects, subjecting them to catastrophic tidal forces that could tear them apart. The concept of a black hole's event horizon is perhaps one of the most mind-bending aspects of these mysterious giants. This boundary, once crossed, marks the point of no return, a place from which not even light can escape. As objects approach the event horizon, they experience strange and bewildering phenomena. To an outside observer, it appears as though time itself slows down for anything crossing that threshold. The object seems to freeze, stretching and dimming, yet it continues its inexorable journey toward oblivion. Once it crosses the event horizon, it is lost forever, its fate sealed by the black hole's impenetrable gravity. Adding to the mystery of Taun 6118 is the theory of Hawking radiation, proposed by physicist Stephen Hawking. According to this groundbreaking idea, black holes are not completely black. Instead, they emit tiny amounts of radiation due to quantum effects. This leads to the fascinating and paradoxical possibility that black holes might eventually shrink and evaporate over time. However, this raises a critical question. What happens to the information that a black hole absorbs? Does it disappear forever, or is it somehow preserved in ways we cannot yet understand? This conundrum challenges our very notions of physics, particularly the concept of information and its conservation in the universe. Beyond the gravitational forces and the mysteries of Hawking radiation, TON 6.18 is also surrounded by an accretion disk of swirling gas and dust. As this material spirals toward the black hole, it heats up to extreme temperatures, emitting bright radiation that we can observe from Earth. These jets of energy are a key tool for studying black holes from a safe distance, allowing scientists to glimpse the behavior of these celestial behemoths without crossing their event horizon. One of the most intriguing questions surrounding TON 618 is its origin. How did such a massive black hole come into being? Was it the result of a singular collapse of a massive star, or could it have formed through the merging of smaller black holes over time? These questions continue to puzzle scientists and fuel ongoing research. The very existence of TON 618 challenges our understanding of the universe, as it forces us to rethink everything we know about gravity, time, and the nature of reality itself. In the depths of space, another black hole system, OJ 287, presents a different kind of mystery. At its heart, this system contains two supermassive black holes orbiting each other in a cosmic dance. One of these black holes is significantly larger than the other and is surrounded by an accretion disk of gas and dust. As this matter spirals inward, it heats up and emits light, creating bright eruptions that we can observe from Earth. But what sets OJ 287 apart is the predictability of these eruptions. Unlike the random outbursts typically associated with black holes, the eruptions in OJ 287 occur at regular intervals, almost like clockwork. This rhythmic pattern is the result of the gravitational interactions between the two black holes. As the smaller black hole moves closer to the larger one, it disturbs the accretion disk, leading to bursts of energy and light. These predictable outbursts give OJ 287 an eerie sense of life, as though it is beating like a cosmic heart. The regularity of these eruptions not only provides valuable insights into the mechanics of black hole behavior, but also offers a unique opportunity to test our theories of gravity. The periodic bursts of energy from OJ 287 also highlight the intricate interplay between celestial bodies, demonstrating how the gravitational forces between two black holes can create a rhythm that echoes across vast distances. This phenomenon serves as a reminder that the universe operates in grand cycles, where order and chaos coexist in ways that we are only beginning to understand. Each burst of light from OJ 287 is a snapshot of this cosmic dance, a glimpse into the hidden forces that shape the fabric of space and time. As we peer into the shadows of these black holes, we are forced to confront the unknown. The mysteries of TON 618, OJ 287, and other supermassive black holes reveal a universe far more complex and terrifying than we could ever have imagined. These cosmic giants, with their insatiable appetites and incomprehensible power, serve as a reminder of the vastness of space and the unknown dangers that lie hidden in the darkest corners of the universe. The precise mechanics behind the rhythmic outbursts observed in distant galaxies remain a mystery. Scientists are still uncertain whether these eruptions are driven by gravitational interactions between massive objects or if they reveal more intricate behaviors, such as the consumption of gas or stellar debris. Each of these explosive events provides a fleeting window into the extreme forces at play, offering critical clues about the life cycles of stars and the complex relationships between immense gravitational forces. However, despite the wealth of data gathered from these phenomena, current scientific models still struggle to fully explain them. The intensity and unpredictability of the bursts only add to the complexity, leaving researchers with more questions than answers. What triggers these eruptions? How can such violent events occur in such a confined space? Understanding these periodic outbursts is vital, not only for expanding our knowledge of black holes, but also for deepening our understanding of the very fabric of our universe. These eruptions, with their immense power and unpredictable nature, challenge existing models of physics. The mystery they present captivates astronomers, fueling the ongoing quest to decode the cosmic puzzle hidden within binary black hole systems. One such system is OJ 287, a bright and active galaxy located millions of light years from Earth. This galaxy is famous for its extraordinary outbursts, which result from the collision of supermassive black holes at its center. To understand the chaos unfolding within OJ-287, imagine a bustling city where violent interactions create a form of cosmic disorder. In this analogy, the two supermassive black holes act as chaotic forces, spiraling toward each other in an endless cosmic dance. As they approach one another, they generate immense gravitational forces, creating disturbances that ripple through both their immediate surroundings and vast distances across the cosmos. These gravitational upheavals manifest as bursts of light and energy, a consequence of the gas and dust that are compressed and heated as they get pulled into the black holes. This process is similar to how clashing vehicles at an intersection can generate loud noises, sparks, and chaos. Each outburst from OJ-287 can be so intense that it rivals the brightness of an entire galaxy, underscoring just how fierce these cosmic interactions are. Additionally, these energetic explosions can create shockwaves, akin to ripples spreading across a pond after a stone is thrown into it. This highlights how a single event, seemingly contained within a galaxy, can have far-reaching consequences that extend across the universe. The violent upheavals within OJ-287 are not merely local occurrences. They serve as a testament to the vast and powerful effects of gravity and energy on a cosmic scale. These interactions reveal the delicate and complex dynamics that govern the universe, shedding light on the processes that shape galaxies, and by extension, the very fabric of the cosmos itself. Moving closer to home, we turn our attention to Sagittarius A Sotha, the supermassive black hole located at the heart of our Milky Way galaxy. This black hole has profound implications, not just for astrophysics, but also for our broader understanding of the universe. The presence of such an immense object suggests that there is an intricate link between galaxies and black holes. This relationship may hold the key to understanding how galaxies evolve over time. The gravitational pull of a supermassive black hole plays a pivotal role in shaping the motion of stars and gas in its vicinity, drawing them into orbit around it. With a mass millions of times greater than our Sun, Sagittarius A exerts a tremendous influence on the Milky Way. Its gravity acts as an anchor, helping to hold the galaxy together and ensuring that stars continue to orbit around it. The motion of these stars, particularly those that reside in close proximity to the black hole, offers astronomers valuable insights into the nature of both the black hole itself and the surrounding environment. As scientists observe the orbits of these stars, they are able to gather clues about the characteristics of the black hole, such as its size, mass, and the structure of the surrounding region. The existence of Sagittarius A also raises compelling questions about the very nature of black holes and their relationship with the fabric of space-time. According to Albert Einstein's theory of general relativity, gravity behaves in ways that can bend light and even affect the passage of time near supermassive black holes. This makes Sagittarius A a natural laboratory for studying extreme gravitational forces and the bending of light, pushing the boundaries of our understanding of physics. As matter is drawn toward Sagittarius A, intense radiation is emitted, which can be detected by powerful telescopes. These observations provide scientists with a deeper understanding of the processes that govern black holes and their influence on surrounding matter. More broadly, the existence of Sagittarius A at the center of our galaxy serves as a reminder of the vastness and complexity of the universe. Living in a galaxy with such a powerful force at its core fuels our curiosity about the mysteries that lie beyond our world. It serves to deepen our appreciation for the intricate dance of celestial bodies, a cosmic choreography that stretches across time and space. To truly comprehend the magnitude of Sagittarius A, one must imagine it as the center of a swirling vortex, where the gravitational pull is so strong that it influences everything around it, including our own solar system. Located approximately 26,000 light-years away, this supermassive black hole exerts a profound gravitational force on nearby stars and objects, creating a vast gravitational well that impacts the orbits of stars in its vicinity. Over long periods of time, this pull can cause significant changes to the trajectories of stars as they pass near the black hole. These alterations to stellar orbits could, in turn, have a profound effect on the stability of star systems, including our own. Imagine a crowded hall where people jostle and bump into each other. A sudden collision can set off a chain reaction, causing multiple individuals to be affected. Similarly, a star passing too close to Sagittarius A could disrupt its orbit, sending other stars spiraling out of their stable paths. The consequences of such an interaction could lead to a chaotic environment in the Milky Way, with far-reaching effects across the galaxy. One such effect could involve the Oort cloud, a vast region of icy bodies that surrounds our solar system. If a star were to pass too close to Sagittarius A, its gravitational influence could disturb the Oort cloud, sending comets and other objects hurtling toward the inner solar system. This could increase the likelihood of collisions with planets, including Earth, raising the potential for catastrophic impacts. Over much longer timescales, the gravitational dynamics of Sagittarius A may even contribute to a gradual shift in the structure of the galaxy itself. This subtle yet persistent force could reshape the Milky Way, altering its shape and the distribution of stars within it. While such changes might take billions of years to manifest, they serve as a reminder of the ongoing, dynamic nature of the universe, where even the most established cosmic structures are in a constant state of flux. The presence of Sagittarius A F* challenges our understanding of time and space, illustrating the powerful, far-reaching influence of supermassive black holes on the galaxies they inhabit. Over immense periods of cosmic time, the gravitational influence of Sagittarius A, the supermassive black hole at the heart of the Milky Way, could gradually alter the very structure of our galaxy. This cosmic force, immense and ever-present, pulls on the stars and matter surrounding it, guiding them toward its powerful center. As stars spiral inward, they may eventually collide, resulting in dramatic stellar mergers. Others, however, may be flung far from the galactic center, ejected into the vast emptiness of intergalactic space, where they will wander alone, lost to the gravitational confines of the Milky Way. If, by some chance, our solar system were to travel along a trajectory that led us towards such a catastrophic encounter, we would find ourselves entering a perilous and unstable region of the galaxy. This scenario would undoubtedly pose great challenges for life on Earth, as we would be subjected to the unpredictable forces of the galactic center. Yet, while Sagittarius A/ holds dominion over its immediate surroundings, its gravitational reach stretches far beyond its direct vicinity. The complex gravitational interactions it generates over millions, even billions of years, have the potential to alter the galaxy in ways we are only beginning to understand, reminding us of our fragile place within the sprawling, ever-changing cosmic dance of the universe. At the heart of our galaxy, Sagittarius A is the source of both awe and mystery. A supermassive black hole, it exerts an irresistible pull on anything that ventures too close. This enigmatic entity is surrounded by a dazzling array of phenomena that seem almost otherworldly, as though plucked from the darkest corners of the universe. As matter falls toward this cosmic giant, it forms a swirling accretion disk of gas, dust, and other stellar debris. The material within this disk moves at mind-boggling speeds, generating extreme heat due to friction and the immense gravitational forces at play. The result is a spectacular release of energy, radiation so intense that it can outshine entire galaxies. This powerful burst of light acts as a cosmic beacon, casting an eerie glow that illuminates the vastness of space, hinting at the boundless energy generated by the black hole's relentless hunger for matter. However, Sagittarius A does not simply consume. It also alters the fate of everything around it. Stars in its vicinity feel the tug of its gravity, and many are pulled into highly elliptical orbits that bring them perilously close to the black hole's event horizon. Some stars seem to vanish entirely, their fate sealed as they are swallowed by the infinite darkness, fueling speculation about what becomes of them in the black hole's heart. This loss creates an unsettling feeling, as though they are being consumed by a force beyond comprehension. In addition to its gravitational pull, Sagittarius A's Frystyle generates powerful jets of energy that shoot outward from the regions surrounding the black hole. These jets, composed of charged particles, move at nearly the speed of light, extending far into the depths of space. These colossal outflows serve as a dramatic reminder of the immense power exerted by the black hole, demonstrating that Sagittarius A Star is far from a simple void, but rather an active force that shapes and molds its surroundings. The interplay of these ghostly phenomena is a testament to the awe-inspiring and unpredictable forces of nature at work, revealing an unfathomable power that warps the very fabric of space-time. The extent of its influence on nearby stars, planets, and even entire galaxies challenges our understanding of the universe, constantly reshaping our perception of what is possible in the cosmos. Similarly, across the universe, M87 Harancharo, the supermassive black hole located at the center of the galaxy M87, stands as a relentless force of cosmic destruction. Known colloquially as the relentless devourer, M87 is an object of great fascination and study, capturing the attention of astronomers and scientists alike. The gravitational forces exerted by M87 are so intense that nothing, not even light, can escape once it ventures too close, creating a one-way trap where anything that crosses the event horizon is doomed to be drawn in. This effect creates an image of the black hole as a cosmic vacuum cleaner, its insatiable appetite capable of consuming stars, gas clouds, and anything else that strays within its reach. One of the defining characteristics of M87 Shri is its enormous accretion disk, a swirling maelstrom of gas, dust, and stellar remnants that spirals toward the black hole. As the material gets closer, it heats up from the intense friction, emitting radiation visible across vast distances. This energy not only powers the formation of a luminous disk around the black hole, but it also leads to the generation of high-speed jets of particles that shoot out from the poles of the black hole. These jets, extending far into space, offer a stunning spectacle for astronomers and provide insight into the extraordinary forces at play in the heart of M87. The true scale of M87's destructive power is underscored by its size. As one of the largest known black holes, it has the capacity to consume entire stars and enormous clouds of gas. Over time, this voracious appetite fundamentally reshapes the galaxy in which it resides, altering its structure and dynamics. M87 Shri embodies the concept of cosmic transformation. Its relentless consumption of matter drives the growth and evolution of its host galaxy. In doing so, it serves as a chilling reminder of the ultimate power of black holes to reshape everything they encounter. The capture of the first ever image of M87 Shri was a monumental achievement in the field of astronomy, marking a milestone in our understanding of these enigmatic objects. For years, black holes, particularly supermassive ones like M87 Tajner, were thought to be theoretical constructs, their existence only implied by the behavior of nearby stars and gas. But the historic image captured by the Event Horizon Telescope provided a tangible representation of what had once been a mere mathematical abstraction. In the image, scientists observed a dark shadow surrounded by a bright ring of light, a visual manifestation of the black hole itself. The light emitted by the hot gas and dust spiraling toward the black hole reached speeds that caused them to glow, creating a distinct ring of brightness. This image confirmed the presence of M87 Shri, validating long-held theories about the nature of supermassive black holes and providing new insights into their structure. It revealed that black holes are not just mysterious voids, but active, dynamic objects with a profound impact on their surroundings. The discovery also deepened our understanding of how black holes grow and evolve over time, and how their interactions with nearby matter can shape entire galaxies. More importantly, it offered an unprecedented view into the heart of one of the universe's most elusive and powerful forces, demonstrating that these celestial giants are not just theoretical anomalies, but real, tangible entities that play a central role in the cosmos. However, it also sparked both fear and fascination. The realization that these immensely powerful entities exist within our universe, capable of consuming everything in their vicinity, is both awe-inspiring and unsettling. The phenomenon of supermassive black holes presents a chilling juxtaposition: the quiet, unyielding force they exert versus the boundless wonder they inspire. Beyond being a mere photograph, this representation opened up a floodgate of questions. What is the role of these cosmic giants in the grand scheme of galactic evolution? And how do they shape the fate of the galaxies they inhabit? These supermassive black holes are not just isolated objects of study, but central figures in the unfolding drama of cosmic history. Their gravitational influence is so vast that they have the potential to change the trajectory of entire galaxies. They serve as the silent rulers of their domains, with their presence often felt only through the subtle motions of the stars that orbit them and the extreme forces they unleash. These enigmatic behemoths, lurking in the darkest corners of space, compel us to reconsider our understanding of the universe's structure and its evolution over cosmic time. One of the most striking features of supermassive black holes is the mysterious jet of high-energy particles that emanates from them, such as the one observed at the center of the galaxy M87. Imagine, if you will, a gigantic vacuum cleaner in space, one that sucks in everything around it and then violently expels energy in the opposite direction. This jet, which stretches vast distances out into the depths of space, is composed of particles traveling at nearly the speed of light, illuminating the dark void of space in ways that were once unimaginable. The creation of these jets is a result of the black hole's intense gravitational pull, combined with the powerful magnetic fields surrounding it. As gas, dust, and other material are drawn toward the black hole, they are subjected to extreme forces, causing them to spiral inward at incredible speeds. In the process, some of this material is heated to such high temperatures that it becomes energized enough to be expelled outward, forming a jet of particles traveling across the cosmos. These jets are not just visually spectacular phenomena, they hold the key to understanding some of the most profound mysteries of black holes. They offer researchers a unique opportunity to study the extreme conditions near a black hole, places where gravity, magnetism, and high-energy environments come together in a way that is not replicable anywhere else in the universe. The particles in these jets interact with the interstellar medium, sometimes triggering shock waves that lead to the formation of new stars. By studying the composition of these particles, scientists gain crucial insights into the fundamental forces that govern the cosmos, allowing them to refine our understanding of gravity, magnetism, and the physics of extreme environments. The M87 jet is, in essence, a cosmic laboratory. It reveals the complex interactions of matter and energy at one of the most extreme locations in the universe. But these jets also hold implications for something even more significant: the evolution of galaxies. It is believed that the energetic particles ejected by black holes like the one in M87 may influence the formation of stars in their surrounding galaxies. By altering the temperature and composition of the gas in these regions, these jets can either suppress or encourage the birth of new stars, potentially altering the entire life cycle of the galaxy. In this way, the study of supermassive black holes, through phenomena such as their jets, becomes essential to understanding how galaxies form and evolve. The M87 jet acts as a bridge between two realms: the deep, mysterious nature of black holes themselves and the broader galactic structures in which they reside. It offers a rare glimpse into the heart of these cosmic giants and the profound impact they have on the evolution of the universe itself. A particularly fascinating case in this narrative is the galaxy NGC 1277, which has drawn the attention of astronomers due to its unusually large black hole. Imagine for a moment the center of this galaxy as a vast gravitational well, a point in space where an immense concentration of mass warps the fabric of the cosmos itself. This black hole is not just a small, insignificant point in the galaxy. It represents a significant portion of the galaxy's total mass. It is a defining feature of NGC 1277, one that sets it apart from most other galaxies in the universe. What makes NGC 1277 particularly intriguing is the delicate balance it maintains between this colossal black hole and the stars that orbit it. The black hole's influence extends across the entire galaxy, shaping the motion of the stars within its gravitational grasp. It is as if the black hole acts as an anchor at the center of the galaxy, its massive size dictating the structure and movement of the entire galactic system. The stars closest to the black hole move in much the same way as planets orbit a star, but their orbits are far faster due to the immense gravitational pull exerted by the black hole. The history of this black hole is equally fascinating. It is likely that it began its life as a small black hole and one that gradually grew over billions of years by drawing in gas, dust, and even entire stars from its environment. At some point, it may have merged with other black holes, further increasing its size. This slow accumulation of mass hints at a long and tumultuous history, one that reveals how black holes can evolve and expand, sometimes in ways that remain hidden from view, without any outward signs of violent activity. The black hole at the center of NGC 1277 silently dominates its galaxy, shaping the fates of the stars around it while remaining largely invisible to us. The study of such galaxies and their black holes is crucial to understanding the larger cosmic picture. It allows us to gain insights into the forces that drive the evolution of galaxies and to appreciate the fundamental role that supermassive black holes play in shaping the universe. NGC 1277 serves as a reminder that the forces governing the cosmos are often hidden from view, lurking in the shadows of space, quietly influencing the paths of galaxies without anyone fully realizing the extent of their power. But NGC 1277 also raises unsettling questions about the formation of black holes in the early universe. Traditionally, scientists have believed that black holes grow slowly over time, gradually accumulating mass through the merger of smaller black holes, the absorption of gas, and the consumption of stars. Yet, the black hole at the center of NGC 1277 is disproportionately large for its host galaxy, suggesting that something unusual occurred early in its history. This anomaly challenges our conventional understanding of how black holes evolve, prompting a re-examination of the processes that may have taken place in the early universe. How did such a massive black hole form so rapidly? Did it begin its life in a way that is radically different from the way most black holes form today? One theory is that black holes in the early universe may have grown at an accelerated rate, possibly due to the conditions that prevailed in the cosmos shortly after the Big Bang. Could these early black holes have formed from the collapse of massive stars, merging together to create supermassive entities much earlier than expected? Or was there some other factor at play? An unknown process that allowed black holes to grow far faster than they do today. Moreover, the existence of such an enormous black hole raises questions about its effects on the surrounding galaxy. With so much mass concentrated in one location, how does it influence the formation of new stars? Could the black hole's gravitational pull be so strong that it prevents the galaxy from forming new stars altogether? This would create an imbalance, where the star-forming processes that drive the evolution of galaxies are stifled by the very presence of the black hole. Lastly, the sheer size of this black hole challenges our understanding of the early galaxies themselves. Did these ancient galaxies form in a fundamentally different way from what we currently believe? Were their environments more chaotic, their conditions more conducive to the rapid growth of black holes? These questions lie at the heart of the mysteries surrounding NGC 1277, a galaxy that, in many ways, forces us to rethink our assumptions about the formation and evolution of the universe. In the end, NGC 1277 stands as a monument to the unknowns of cosmic history. It serves as both a source of inspiration and a challenge to our understanding of the universe's past. The questions it raises are not just academic. They strike at the very heart of how galaxies and black holes evolve together and how the universe has unfolded over the course of billions of years. Studying NGC 1277 and galaxies like it is essential for reshaping our understanding of the cosmos, helping us peer into a distant past that may forever remain out of reach. At the heart of NGC 1277 lies an entity so massive that it exerts a profound influence over its surroundings. This supermassive black hole is more than just a gravitational anomaly. It is a powerful force that alters the very fabric of the galaxy itself. Its immense gravitational pull can slow down the formation of new stars. As gas clouds, the essential building blocks of stellar creation, get stripped away by the black hole's overwhelming gravity, the galaxy is left with fewer opportunities for new stars to form. Over time, this scarcity of new stellar births causes the galaxy to slowly age. The existing stars burn out, and the overall brightness of NGC 1277 fades, leaving behind a once vibrant collection of stars in a gradual state of decay. The interplay between this black hole and the stars surrounding it creates a chilling environment, a dynamic where survival becomes increasingly unpredictable, and the consequences of these forces are perilous. NGC 1277, while a cradle for some of the most fascinating cosmic phenomena, serves as a limiting factor for stellar evolution, halting the birth of stars and shaping the galaxy's future for billions of years to come. It is both a source of destruction and a profound influence on the life cycle of the galaxy, reminding us of the invisible yet undeniable forces at play in the universe. Similarly, Centaurus A offers another powerful example of how supermassive black holes can define the dynamics of galaxies. Located about 12 million light-years away from Earth, Centaurus A is home to a black hole at its core surrounded by swirling clouds of gas and dust. As material spirals toward the black hole, some of it doesn't get sucked in. Instead, it is heated to extreme temperatures, causing it to explode outward in two colossal jets that shoot out from the black hole's poles. These jets are akin to cosmic fountains, streams of charged particles and magnetic fields blasting through space at nearly the speed of light. The jets extend for vast distances, sometimes spanning thousands of light years, and as they travel through the surrounding gas and dust, they heat it up, causing it to glow brightly. This interaction creates a visible structure in the galaxy that can be seen across vast distances of space. The power of these jets has far-reaching consequences. They can both trigger and suppress star formation in different regions of the galaxy, almost like a cosmic sculptor shaping the environment. The scale, energy, and speed of these jets make Centaurus A one of the most fascinating and dramatic examples of a galaxy influenced by its central black hole. The way in which these jets interact with the surrounding gas and dust marks a violent yet awe-inspiring feature of the cosmos, adding another layer to the complex narrative of cosmic evolution. In fact, Centaurus A is a textbook example of how black holes can act as both creators and destroyers. As the material from the galaxy is drawn into the black hole, it generates vast amounts of energy, emitted in the form of X-rays and gamma rays, two types of ultra-high energy radiation that tell astronomers that something extraordinary is happening at the center. These emissions suggest not only the active nature of the black hole, but also the formidable forces at play in reshaping the galaxy around it. The immense energy released from the black hole is so powerful that it can alter the formation of stars and the overall structure of the galaxy. The black hole in Centaurus A serves as a reminder that, in the universe, the boundaries between creation and destruction are often blurred. Moreover, this galaxy showcases the complexity of black holes. While they are typically known for their destructive nature, they are also capable of acting as agents of change, altering the dynamics of entire galaxies. Some regions of Centaurus A's vast expanse are subjected to shock waves from the black hole's energetic outflows, which can actually trigger new star formation. However, other areas suffer destabilization as the intense radiation strips away gas, disrupting the natural processes of stellar birth. This dual role of creation and destruction highlights the central paradox of black holes. They are both magnificent forces that shape the universe and terrifying agents of entropy. Far beyond the reach of Earth's gaze lies IC 111, a galaxy that houses one of the largest known supermassive black holes. As the galaxy's gravitational anchor, this black hole exerts an overwhelming influence on its surrounding stars and matter. IC 111's black hole is not just massive, it's a behemoth, so powerful that it distorts the very fabric of space itself. It's hard to imagine, but its immense mass warps space-time to such a degree that it significantly alters the motion of entire clusters of galaxies. What sets IC 111 apart from other galaxies with supermassive black holes is the sheer scale of its central black hole. While many galaxies have sizable black holes, none seem to match the staggering size of IC 111's. This black hole, believed to have been growing for billions of years, serves as a colossal gravitational well. Its influence stretches far beyond the galaxy's core, affecting the movement of countless stars and creating a gravitational field so powerful that it dominates the galaxy's entire structure. The black hole remains unseen by traditional telescopes. It is entirely dark, and its presence is inferred only through its effects on the galaxy around it. The massive gravitational field of IC-111's black hole alters the behavior of stars in its vicinity, pulling them into its orbit, or in some cases, devouring them entirely. This celestial vacuum cleaner doesn't simply take in dust and gas, it engulfs everything within its grasp, including entire stars. The eerie presence of such a monstrous entity at the core of a galaxy raises unsettling questions about the ultimate fate of all matter. As stars and gas spiral ever closer to the event horizon, the very laws of physics bend under the black hole's influence, creating a reality where time itself begins to slow down. The closer an object gets to the black hole, the more stretched and distorted it becomes, turning space-time into a warped and eerie mirror of our own universe. This phenomenon, known as gravitational time dilation, introduces a psychological element to the terror of black holes. The immense gravitational pull distorts reality itself, making the surroundings increasingly surreal and dangerous. In the heart of IC-111, reality itself is twisted, and the familiar laws of the universe become increasingly difficult to comprehend. The presence of this black hole evokes both awe and fear, underscoring the terrifying power that exists in the cosmos and the mysteries of the universe that remain, as yet, beyond our understanding. IC-111's black hole serves as a haunting reminder of the extreme and often terrifying forces at work in the universe. Its sheer size challenges our understanding of cosmic scale, and the gravitational forces it generates reveal a universe that is far more hostile and enigmatic than we can ever truly grasp. The size and power of this black hole reshape the very nature of the galaxy itself, casting a long shadow over the stars and planets that orbit it. Yet, despite the fearsome nature of this entity, it also invites us to reconsider what we know about the universe, pushing the boundaries of our understanding and filling us with both wonder and dread at the unfathomable forces that govern the cosmos. The immense distance that separates us from IC-1101 amplifies the eerie nature of this cosmic giant. Situated more than 1 billion light-years away, it stands as an awe-inspiring, yet unsettling reminder of our vulnerability in the vastness of the universe. In the grand expanse of the cosmos, we are nothing more than fragile specks of dust, drifting precariously amidst giants like this supermassive black hole. The mere realization that such colossal entities exist somewhere in the endless void forces us to reflect deeply on our place in the universe, evoking a profound sense of humility. It is a stark reminder of the fine line that divides curiosity and fear when we look out into the infinite night of space. IC-1101's black hole is not just a marvel of size and scale. It is an ominous symbol of the unimaginable forces that shape our universe, stirring both fascination and trepidation about what lies beyond the boundaries of our terrestrial existence. At the heart of its galaxy, this black hole has unique spectral attributes that offer a rare glimpse into the mysterious processes unfolding within. As light approaches such a black hole, most of it is inevitably drawn into its gravitational pull, but a fraction can escape. This escaping light provides invaluable clues about the black hole's environment and its effects on its surroundings. One key phenomenon associated with black holes is the emission of radiation, and particularly in the form of X-rays. As gas and dust from nearby stars spiral inward, they become subject to tremendous gravitational forces, causing them to heat up to extreme temperatures. This superheated material emits intense X-rays, detectable by astronomers and serving as a critical source of information about the black hole's mass and the complex dynamics at play around it. In addition to these X-ray emissions, black holes also influence the light that filters through their vicinity, shaping what is known as an accretion disk. The light emitted from this disk can display a wide range of colors, depending on the speed and temperature of the particles swirling around the black hole. These light spectra often feature broad emission lines, revealing the high velocity and turbulent motion of gas near the event horizon. Furthermore, the presence of black holes affects the movement of stars and gas within their galaxies, subtly altering their trajectories. This gravitational influence can be observed in the shifting spectral lines of nearby stars, offering evidence of how black holes can manipulate the very structure of their host galaxies. Each spectral reading is a piece of cosmic history, unraveling the dynamic relationship between black holes and the evolution of galaxies, star formation, and the architecture of the universe itself. Take, for instance, the supermassive black hole designated H1A21 plus 643. Situated at the heart of its galaxy, this black hole stands as a vivid example of the relentless and consuming nature of these cosmic titans. Imagine an insatiable vacuum cleaner forever devouring gas, dust, and even stars that venture too close. As matter spirals inward, it forms a glowing accretion disk, where the material is heated to unimaginable temperatures by friction and intense gravitational forces. This process generates blinding light, visible across vast stretches of space, offering a stark demonstration of the terrifying power black holes wield over their surroundings. The destructive potential of black holes is starkly highlighted when nearby objects pass the event horizon, the point of no return. Once within this region, matter is drawn inexorably into the black hole, vanishing from our universe without a trace. This relentless gravitational grip illustrates the destructive capabilities of black holes, creating a realm where the conventional laws of physics seem to break down entirely. The immense gravitational forces not only consume matter, but also impact the very fabric of space and time around them. Moreover, the growth of black holes like H1A21 plus 643 can dramatically reshape their surrounding galaxies. As they pull in matter, they influence the movement of stars and gas, often altering the rate at which new stars are born and determining the fate of countless celestial bodies. The immense forces at work here serve as a reminder of the dynamic and often violent nature of the universe, where creation and destruction coexist in a delicate, ever-changing balance. Quasars, which are among the brightest objects in the universe, provide another fascinating glimpse into the workings of supermassive black holes. H1A21 plus 643 is no exception. Picture a point in space so incredibly bright it outshines an entire galaxy, emitting an almost unimaginable amount of energy. This dazzling radiance is the result of gas and dust spiraling into the black hole, where friction and gravitational forces cause the material to heat up and radiate energy across a wide spectrum, from radio waves to visible light and even X-rays. This intense energy release makes quasars some of the most luminous objects known to science, a clear signal of the immense power of these cosmic engines. The brightness of H1A21 plus 643 offers more than just a measure of its energy output. It serves as a window into the overwhelming gravitational forces that shape the black hole's environment. As material accelerates toward the event horizon, it is ejected from the black hole's poles in the form of relativistic jets, streams of particles moving at nearly the speed of light. These jets stretch across vast distances, illuminating the space around them with high-energy emissions that can be detected across millions of light years. The very existence of H1A21 plus 643 challenges our understanding of the relationship between black holes and galaxies. Its extraordinary brightness highlights the fierce energy hidden within such a supermassive black hole, offering insights into the processes that govern the evolution of galaxies and black holes. Even though it resides millions of light years away, H1A21 plus 643 provides a critical opportunity to observe and understand the cosmic forces at play on the grandest scale. The immense size of H1A21 plus 643, a colossal black hole at the center of a distant galaxy, offers essential clues about the growth of supermassive black holes over time. Imagine the sheer scale of a black hole that can consume entire stars, drawing vast amounts of matter toward it. The scale of this black hole defies our traditional understanding, suggesting that supermassive black holes may not only grow steadily, but could experience rapid bursts of growth during specific cosmic events. These events may involve mergers with other black holes or the accumulation of gas from their surroundings. H1A21 plus 643 serves as a vital case study, helping scientists explore how supermassive black holes can evolve faster and grow larger than we once thought possible. The massive size of this black hole challenges existing theories about the formation of such entities, opening up new avenues for understanding the complex processes that govern the birth and growth of these celestial giants. By examining the evolution of H1E21 plus 643, astronomers can gain a deeper understanding of how black holes shape the universe over time, influencing the formation of galaxies, the movement of stars, and the very structure of the cosmos itself. In the end, black holes like H1E21 plus 643 not only represent the raw power of the universe, but also serve as key markers in the ongoing cosmic narrative. Through their spectral attributes, their consumption of matter, and their influence on their surroundings, these titanic forces remind us of the vast, mysterious forces at play in the universe, forces that continue to shape the cosmos in ways we are only beginning to understand. The discovery of the massive black hole in the distant galaxy H1A21 plus 643 has sparked a new wave of excitement and intrigue among researchers, forcing them to reconsider long-standing theories about the relationship between black holes and the galaxies that host them. This discovery challenges existing models, suggesting that the dynamic interactions between a black hole and its host galaxy could play a crucial role in the black hole's growth, as it gathers the necessary materials from its surroundings. As scientists examine this cosmic giant, they aim to refine their understanding of how supermassive black holes form and evolve, as well as how the environments around them evolve in response. The black hole at the center of H1A21 plus 643 is not just a run-of-the-mill supermassive black hole. It stands as a fascinating object that captivates astronomers with its extreme features. It's surrounded by an accretion disk, a swirling mass of gas and dust spiraling around it at breakneck speeds. As these materials rush toward the black hole, the friction and immense pressure cause them to heat up, generating enormous amounts of energy. The result is a shining beacon, making H1A21 plus 643 one of the brightest objects in the universe. However, what sets this black hole apart from others is its ability to shoot jets of high-energy particles and radiation from its poles, traveling at nearly the speed of light. These energy jets extend far out into space, creating shock waves that ripple through the surrounding cosmic landscape, affecting the material in their path. Imagine a cosmic fireworks display where brilliant beams of light and energy explode from the heart of the black hole, casting illumination into the deepest corners of the universe. These jets not only light up vast regions of space, but they also have significant implications for the surrounding galactic structures. The gravitational pull near the event horizon of H1E21 plus 643 is so intense that it stretches and compresses anything that dares to venture too close. This phenomenon, known as spaghettification, is a result of the immense tidal forces present in such a strong gravitational field. Objects approaching the black hole experience a tremendous difference in gravitational force between their near and far sides, causing them to be stretched out into elongated forms, like strings of spaghetti. It's a grotesque yet fascinating aspect of these cosmic monsters, highlighting the power that such black holes wield over their environment. The sheer size of the black hole itself, which can weigh millions or even billions of times more than our sun, contributes to the extraordinary phenomena we observe. As it draws in more material, gas, dust, and even stars, it continuously fuels the black hole, resulting in energetic outflows that influence not only nearby stars and gas clouds, but also play a critical role in the formation and evolution of entire galaxies. These energetic behaviors are a reminder of the incredible forces at play within the universe, revealing how black holes like the one at the center of H1A21 plus 643 can shape the cosmos. Moreover, the black hole at the heart of this galaxy offers astronomers a deeper look into the processes that govern the universe's most enigmatic objects. By studying these cosmic giants, scientists are piecing together a more complete picture of the life cycle of supermassive black holes, how they form, grow, and interact with their host galaxies. Every new discovery brings us closer to understanding the evolutionary story of the universe, shedding light on the intricate processes that have shaped the cosmos as we know it. S54 plus 81, another galaxy located billions of light years away, contains a similarly impressive supermassive black hole. This black hole, like H1A21 plus 643, is surrounded by an accretion disk, but what makes it particularly extraordinary is its ability to emit incredibly bright radiation, resulting in the formation of a quasar. A quasar is a highly energetic region at the center of a galaxy, powered by the supermassive black hole that lies within it. The intense light emitted by quasars allows scientists to study not only the black hole itself, but also the surrounding materials and the space through which the light travels. Quasars like the one in S5 4Plus81 act as beacons of light, allowing us to peer into the farthest reaches of the universe. As this light travels through space, it encounters different materials such as gas clouds and dark matter. Some of this light is absorbed, scattered, or distorted, offering researchers crucial insights into the composition of the universe. Through these interactions, scientists can infer the existence of otherwise invisible components, such as dark matter, that contribute to our understanding of the universe's structure. The light emitted by quasars also provides a glimpse into the surroundings of black holes, what is often referred to as the cosmic environment, revealing the forces and phenomena that govern the distant reaches of space. Even though these quasars are situated billions of light years away, they serve as powerful tools for unlocking the secrets of the universe, offering us a window into both the black holes and the galaxies that house them. As we delve deeper into the mysteries of black holes, we encounter a number of strange and terrifying phenomena. When an object gets too close to a black hole, it is drawn into one of the most intense gravitational fields in the universe. This pull accelerates rapidly as the object nears the event horizon, the boundary beyond which nothing can escape. The gravitational force becomes so intense that it overwhelms any other forces, including the object's own momentum. Imagine pulling a rubber band tighter and tighter until it can no longer stretch any further. The tension becomes unbearable. This is the effect felt by objects nearing the event horizon, as they experience what are called tidal forces. Tidal forces occur because the gravitational pull is stronger on the side of the object closest to the black hole than on the far side. This difference stretches the object out in a process known as spaghettification. Once an object crosses the event horizon, it is lost to the black hole forever, disappearing into the singularity at the center. The singularity is the point where all the mass of the black hole is thought to be concentrated, and gravity becomes infinitely strong. At this point, the laws of physics as we understand them break down, leaving scientists with a perplexing and unsolved mystery. The event horizon acts as a one-way barrier. Once something crosses it, there is no return. The object is pulled into the black hole's interior, where the gravitational forces are so extreme that they warp space and time in ways we can barely comprehend. As we continue to study black holes, we find ourselves at the edge of our understanding of the universe, peering into the unknown. In recent years, the discovery of one of the largest cosmic explosions linked to the black hole in the Euclid cluster has expanded our knowledge of these phenomena. Astronomers first observed unusual energy emissions from the region of space surrounding a supermassive black hole at the center of the Euclid cluster. Using X-ray data from space telescopes, they discovered an unusual cooling pattern in the hot gas surrounding the black hole, something that shouldn't happen under normal conditions. Shockwaves were detected, suggesting that a massive explosion had occurred, sending ripples through the surrounding gas and energy. This explosion, which was detected from vast distances, demonstrated the immense power of black holes. The shockwaves released from the explosion were so intense that they pushed colder gas away from the black hole, significantly altering the dynamics of the surrounding galaxy cluster. This outburst of energy revealed a dramatic and violent side of black holes that most people rarely consider. It served as a stark reminder of the vast, unpredictable power of these cosmic objects, which can create disturbances that ripple across the universe. The discovery of such enormous explosions and energy releases underlines the terrifying and awe-inspiring forces at work in the universe. As black holes consume matter and release jets of high-energy particles and radiation, they shape the environments around them, affecting not only their immediate surroundings, but the galaxies and clusters of galaxies that exist within their gravitational reach. These explosions highlight the incredible power of black holes to influence the structure of space itself, offering a glimpse into the raw, destructive forces that govern the universe. Each discovery about black holes, from their gravitational effects to the spectacular outbursts they create, reveals just how much we have yet to learn about the cosmos. These phenomena, although terrifying, captivate us with their beauty and mystery, reminding us of the complex and violent nature of the universe. As our understanding of these incredible objects deepens, we come closer to unraveling the secrets of the universe's most enigmatic forces. However, this awe-inspiring spectacle also brings with it a profound sense of fear. The sheer might of a black hole is overwhelming, capable of disrupting entire star systems with an ease that is both staggering and terrifying. Should our planet drift too close to one of these cosmic giants, the gravitational forces could tear it apart, annihilating everything in its path. The thought of being consumed by such an immense and seemingly unstoppable force triggers a primal fear deep within us, one tied to the unknown, to the darkness that lies beyond our comprehension. Black holes embody the dual nature of cosmic phenomena. On one hand, they are brilliant and mysterious, and on the other, they carry the terrifying potential for destruction. One of the most astonishing displays of this power comes in the form of the UCAS explosion, a catastrophic event that vividly showcases the extraordinary forces hidden within black holes. Imagine, if you will, a colossal explosion occurring in the heart of a galaxy cluster, releasing energy equivalent to the combined output of millions of suns. The force behind such an explosion reveals just how black holes can unleash mind-boggling levels of energy, transforming everything in their vicinity. But perhaps even more fascinating is the mechanism behind this incredible outburst. At the very core of a black hole lies a singularity, an area where the gravitational pull is so intense that not even light can escape its grasp. When matter falls into a black hole, it does not vanish into nothingness. Instead, much of it is heated to astronomical temperatures before being swallowed whole. This process of heating generates vast amounts of energy, which is then ejected into space in the form of jets of particles traveling nearly at the speed of light. These jets are not just streams of particles, they are destructive forces, creating shockwaves that propagate across intergalactic space. As they interact with surrounding matter and gas, they trigger spectacular bursts of energy. In the aftermath of such an event, new stars can be prevented from forming in the region as the shockwaves sweep through space, disrupting the delicate conditions necessary for stellar birth. The UCAS explosion serves as a vivid illustration of how these jets interact with the larger environment, revealing that black holes are not just passive, isolated voids in space. Rather, they are active players, shaping the evolution of galaxies, affecting star formation and influencing the very structure of the universe itself. The power of a black hole is not merely determined by its mass. It is also a product of the complex dynamics of its environment. Through these cosmic explosions, we begin to understand that black holes are not just terrifying forces of destruction. They are also central to the grand, often chaotic dance of the cosmos. This dramatic event reminds us of the profound complexity of cosmic interactions, where forces collide and intertwine in ways that are unpredictable and beyond human imagination. Each explosion, each jet of particles reveals deeper layers of the universe's mysteries, inviting us to understand more about the most powerful forces in existence. Through these explosions, we gain a glimpse into the very heart of the cosmos, a place where power, mystery, and fear intersect in unimaginable ways. One such black hole, APM 8279+5255, stretches the limits of our understanding. Located in a distant galaxy far beyond the reaches of our own, this black hole is one of the largest known to science, and its size is beyond anything most of us could truly comprehend. To visualize it, imagine a region of space with a mass greater than 1 billion suns, all compressed into an area so small that even light cannot escape its gravitational pull. The very fabric of space and time around this black hole is warped and distorted by its enormous gravity, creating a surreal and almost terrifying environment. Stars in its vicinity do not merely orbit it, they are violently pulled in, their paths changed in dramatic ways. The entire galaxy, in fact, seems to revolve around this colossal force, as if it is the central pivot of an unimaginable cosmic dance. Being near such a massive entity would evoke a deep sense of dread, as if facing a cosmic predator, lurking silently in the shadows of space. Consuming everything in its path, from gas to dust, it relentlessly grows, feeding on the very matter around it. The gas and dust swirling around it form an accretion disk, a chaotic ring of material that glows brightly as it is heated by friction and gravitational forces. This fiery glow signals the presence of the black hole, as it stands as a beacon of its immense and terrifying power. The sheer existence of APM 8279 plus 5255 serves as a stark reminder of how small and fragile we are in the grand scale of the universe. The scale of this black hole is mind-boggling, challenging everything we thought we knew about the nature of space, time, and gravity. It forces us to confront the terrifying reality that the universe is home to forces so vast and so incomprehensible that we are but tiny, insignificant specks in the grand expanse. In the presence of such cosmic giants, we are humbled, reminded that the universe is filled with unimaginable wonders, but also with dangers beyond our understanding. Beyond its size, black holes give rise to an array of astonishing phenomena that only add to their fearsome reputation. Surrounding a black hole is a region known as the accretion disk, a turbulent swirl of gas, dust, and other materials spiraling inward toward the event horizon. As these materials fall into the black hole, they are subjected to extreme friction and gravitational forces, heating up to the point of emitting intense radiation. This radiation, which can be detected in wavelengths such as X-rays, makes the black hole visible against the otherwise dark backdrop of space, revealing its terrifying presence. Furthermore, black holes are capable of producing powerful jets of particles that shoot outward from their poles at nearly the speed of light. These jets are driven by the immense magnetic fields generated by the accretion disk, sending particles hurtling across vast distances. These high-energy jets do not just disappear into the void, they interact with surrounding galaxies, potentially altering the course of star formation and shaping the structure of the galaxy itself. This demonstrates the extraordinary reach of black holes, as their influence extends far beyond their immediate vicinity, affecting the very fabric of the universe. Another phenomenon tied to black holes is the creation of gravitational waves. When black holes collide or merge, they generate ripples in the fabric of space-time, waves that travel outward at the speed of light. These gravitational waves cause tiny distortions in space as they pass through the universe, stretching and compressing it in their wake. The detection of these waves has provided critical insights into the nature of black holes, allowing scientists to observe and study these cosmic giants in ways previously unimaginable. All of these phenomena, the radiating energy from the accretion disk, the explosive jets, and the generation of gravitational waves, combine to forge the fearsome reputation of black holes. They demonstrate not only the destructive potential of these cosmic giants, but also their crucial role in shaping the universe itself. The more we study these effects, the clearer it becomes that black holes are not merely points of no return. They are dynamic engines of change, wielding immense power and influencing the very structure of the cosmos. The discovery of supermassive black holes at the centers of many galaxies has revolutionized our understanding of the universe. These black holes, some of which are millions or even billions of times the mass of our sun, challenge long-held theories about galaxy formation. For a long time, scientists believed that galaxies formed through the slow accumulation of matter. However, the discovery of these massive black holes has forced us to reconsider this view, suggesting that black holes may play a central role in the formation and evolution of galaxies themselves. In this ever-expanding universe, the mysteries surrounding black holes continue to unfold, drawing us deeper into the heart of the cosmos. They remain one of the most fascinating and frightening aspects of our universe, offering both awe-inspiring insights and humbling reminders of how little we truly understand about the vast, uncharted reaches of space. However, these colossal black holes point to a much deeper and perhaps even more critical role they play in the cosmos, shaping their host galaxies from the very earliest moments of their existence. It is as if they serve as invisible anchors, silently pulling the fabric of space around them, dictating how stars, gas, and other cosmic materials gather in their vicinity. At the very core of one such galaxy, known as Home 15A, lies an extraordinary supermassive black hole, a region of space where gravity exerts such a tremendous force that even light itself cannot escape its relentless pull. This black hole's difference feels both overwhelming and eerily ghostly, as it shapes not only the immediate environment around it, but also the grand dynamics of the entire galaxy. The key factor behind this cosmic influence is its extraordinary mass. Imagine an object of unimaginable weight, so massive that it warps the very space-time around it, pulling everything nearby into its powerful gravitational grip. The black hole at the heart of Home 15A is one of the largest ever discovered, containing billions of times the mass of our Sun. This immense mass creates a gravitational force so intense that it profoundly alters the motion of nearby stars, gas clouds, and other interstellar matter. As material spirals toward the black hole, it forms an accretion disk, a violent whirlpool of gas and dust. The friction generated in this disk causes the gas to heat up to mind-boggling temperatures, emitting vast amounts of radiation. This intense energy can shine brightly, even across vast cosmic distances, allowing astronomers to detect its presence despite the darkness at its core. However, at the very center of the black hole lies the event horizon, the boundary beyond which nothing, not even light, can escape. Once any matter crosses this threshold, it is consumed by the black hole, adding to its mass and reinforcing its ghost-like, invisible nature. This creates an intriguing paradox. The black hole itself is imperceptible, hiding in the shadowy depths of space, visible only through its effects on the surrounding stars and gas. Its influence, however, is far-reaching. The black hole at Home 15A doesn't merely affect the immediate area around it. It exerts a force that shapes the entire structure and behavior of the galaxy. Its gravitational pull is a dominant force in determining how stars form and interact, as well as how gas and other materials are distributed across the galaxy. This cosmic architect directs the movements and evolution of the galaxy, pulling strings from its hidden, invisible throne. The combination of this immense gravitational power and the haunting silence of what lies beyond the event horizon gives the black hole a unique and mysterious presence that fascinates astronomers and stirs curiosity among space enthusiasts. Home 15A's supermassive black hole is a striking reminder of the complexity and enigma of the universe. Despite its massive size, this black hole does not shine like a star. It does not emit visible light, nor does it glow like the countless stars that surround it. Instead, its very lack of visibility creates an eerie, unsettling atmosphere, making it seem like a predator lurking just beyond the veil of sight, waiting in the cosmic shadows. The surrounding star cluster, by contrast, is a vibrant display of color, energy, and movement, everything a thriving galaxy should be. But beneath this dynamic display, the black hole exerts a quiet yet unyielding force. It exerts an unseen control over the galaxy, shaping the very fabric of space itself. This idea is deeply unsettling. Black holes, because of their extraordinary density and gravitational power, can pull everything around them into their grasp. Gas, dust, and even entire stars. This gravitational force can lead to catastrophic consequences, destabilizing nearby stars, swallowing celestial objects whole, and fundamentally altering the structure of the galaxy over time. What makes this phenomenon even more disturbing is the fact that we cannot see the black hole itself. We rely on indirect evidence, the movement of stars, the behavior of nearby gas clouds, and the radiation from the accretion disk to understand its presence. This indirect observation creates an eerie sense of uncertainty. We know it's there, exerting its power, but we cannot directly observe the source of this incredible force. The gravitational pull and the quiet, consuming nature of the black hole ignite our imaginations, raising questions that keep astronomers awake at night. What might happen if we ventured too close? Could it strike without warning, consuming everything in its path? Would it disrupt the formation of new stars, throwing the entire galaxy into chaos? This mixture of awe and fear, combined with the mystery of what lies hidden beyond the event horizon, evokes a profound sense of danger and the unknown. Black holes are not just cosmic oddities. They represent the chaotic, unpredictable forces of the universe, forces that are beyond our comprehension and control. They challenge our understanding of space and time, pulling us into a realm where the usual laws of physics seem to break down. The very existence of black holes forces us to confront unsettling questions about the nature of reality itself. In the centers of these dark giants, the laws of physics as we understand them crumble. This is where the concept of a singularity arises, a point of infinite density, where gravity is so intense that it warps the very fabric of space and time, and conventional physics cannot even begin to explain what happens. What we are left with is a gap in our knowledge, a void where our understanding of the universe falters, and we are left to confront the limits of human comprehension. For those who venture too close to these cosmic behemoths, the consequences are dire. Imagine, for a moment, a spacecraft approaching a black hole. As it draws nearer, it is caught in the inescapable grip of the black hole's gravitational pull. Escape becomes impossible. No matter how much thrust the spacecraft generates, it will be pulled inexorably toward the event horizon. There is no return. This sense of helplessness, of being drawn toward an inescapable fate, is what makes black holes so terrifying. They are the ultimate traps in the vastness of space, entities so powerful and so absolute that nothing, not even light itself, can escape. Thus, black holes stand as both symbols of awe and fear in the universe. They represent not just cosmic destruction, but also the mystery and wonder of forces far beyond our current understanding. The very existence of these enigmatic creatures serves as a reminder that the universe is far more strange, complex, and incomprehensible than we can even begin to imagine. In the quiet darkness, black holes continue to lurk, silent giants shaping the cosmos in ways we are only beginning to understand. Moreover, black holes challenge our very understanding of time itself, creating phenomena that defy ordinary experience. As one ventures closer to a black hole, time begins to behave in ways that are utterly strange to anyone observing from a distance. Time slows down dramatically for an observer near the black hole, compared to someone far away. This distortion of time sparks a deep existential fear, raising the unsettling possibility that our everyday experiences of time might be altered in ways that are nearly impossible to imagine. It's as if the very fabric of reality is being bent, reshaping the universe as we know it. The very concept of time, which we typically perceive as a constant flow, becomes warped and malleable near these mysterious cosmic entities. The enigmatic nature of black holes not only stirs scientific curiosity, but also evokes a primal sense of fear, a fear of the unknown. The more we learn about black holes, the more we are confronted with the stark reality that we may understand far less than we think. This imbalance between what we know and what we don't know pulls us in deeper, driving the limits of our exploration. At the same time, the dangers lurking in the heart of these objects constantly remind us of the inherent unpredictability of the cosmos. In their silent majesty, black holes stand as eternal symbols of the vast mysteries that lie beyond human comprehension. They stir both awe and trepidation, urging us forward in our pursuit of knowledge while reminding us of how little we truly grasp about the universe. Take, for instance, the supermassive black hole at the heart of the galaxy, NGC 1600. This behemoth of the cosmos holds a profound yet often invisible sway over the entire galaxy. At the center of NGC 1600 lies a black hole that is millions of times more massive than our own sun, a gravitational force so immense that it dominates the dynamics of the galaxy. This black hole's gravity exerts a silent but undeniable influence, bending the orbits of stars and gas clouds that are caught in its grasp. As objects spiral closer to the black hole, their movements are altered in a subtle cosmic dance, one that reshapes the entire galactic structure over time. The interactions between the black hole and nearby stars can even lead to the formation of new stellar orbits, gently nudging their paths and slowly changing their courses across vast stretches of time. Yet, black holes are notoriously difficult to observe directly. Most of what we know about them comes from studying their effects on the objects around them, rather than from any direct imaging or observation. In the case of NGC 1600, the black hole's influence can be seen in the altered movements of stars and in the overall structure of the galaxy, but this remains a largely invisible force. This subtlety makes measuring the black hole's influence an intricate and sometimes frustrating process for astronomers. Additionally, the supermassive black hole's effects also extend to the rate of star formation within the galaxy. The black hole expels vast quantities of gas from the central region in high-energy bursts known as jets, which travel at nearly the speed of light. This expelled gas would otherwise have been available for the creation of new stars. By siphoning off this material, the black hole indirectly controls the very life cycle of the galaxy, determining how vibrant or quiescent it appears at any given moment. The black hole at the heart of NGC 1600 plays the role of a silent architect, shaping not only the evolution of stars, but also the interstellar medium that fills the galaxy. This influence underscores an essential cosmic truth. The unseen forces lurking at the heart of galaxies can have far-reaching consequences, impacting not just the black hole itself, but the entire environment surrounding it. By studying such interactions, astronomers gain a deeper understanding of the interconnectedness of celestial bodies. They also learn about the delicate balancing act between creation and destruction that occurs on a galactic scale, where forces of immense power simultaneously foster the birth of new stars and inhibit their formation. NGC 1600 is a particularly intriguing case because, despite housing a supermassive black hole at its core, this black hole remains largely hidden from our view. Unlike more active black holes that voraciously consume matter and emit bright radiation visible across vast distances, the black hole in NGC 1600 is dormant. It does not actively pull in gas or dust at a high rate, which means it does not radiate the brilliant light that typically characterizes black holes in their active state. Furthermore, the structure of NGC 1600 itself complicates the task of detecting its black hole. As a giant elliptical galaxy, it has a dense core packed with a vast number of stars, all of which contribute to a bright and cluttered background. The light from these stars often obscures the black hole's presence, making it even harder to spot. This combination of a dormant black hole, a crowded galactic center, and the very nature of black holes, which do not emit light themselves, has allowed the supermassive black hole at the heart of NGC 1600 to remain concealed for so long. Instead of the direct observation of a bright, glowing accretion disk, astronomers have had to rely on indirect methods to detect its existence. Through the careful tracking of stars' orbits and measuring the subtle gravitational effects on their paths, scientists were eventually able to infer the presence and mass of this colossal object. This painstaking process, requiring precise observations over long periods of time, demonstrates how even massive objects in our cosmic neighborhood can remain hidden if they don't conform to the typical profiles of active black holes. The discovery of such a dormant black hole offers new and exciting possibilities for understanding the hidden structures of the universe. It suggests that there may be more of these massive entities out there, lurking in the depths of space, completely undetected. Dormant black holes, while not currently pulling in matter or shining with bright radiation, still exert an immense gravitational influence on their surroundings. The very fact that such a massive object can remain unnoticed for so long raises questions about how many other black holes might be in a similar dormant state, waiting for the right conditions to become active once more. If one enormous black hole can remain hidden, it's entirely possible that there are many more out there, concealed in the vast expanses of the universe. By studying the surrounding environment, astronomers may be able to detect the presence of these dormant giants. Unusual stellar orbits, for instance, may be an indication of a nearby black hole, one whose gravitational pull is subtly shifting the stars around it. This possibility opens up a new realm of exploration, suggesting that the universe may be populated by a vast and largely invisible network of black holes that are currently in a state of inactivity. Understanding this potential abundance could lead to a reevaluation of how black holes form, evolve, and interact with their surroundings. Meanwhile, the supermassive black hole known as SGR A* at the center of our Milky Way galaxy represents another fascinating case. SGR A* is not just another typical black hole. It is distinguished by its immense scale and by the energetic history it carries with it. Unlike other black holes, which are often isolated and quietly devour surrounding matter, SGR A* is believed to have formed from a supernova explosion, a catastrophic event that marked the death of a massive star. The explosion expelled enormous amounts of matter and energy into space, and these energetic remnants still linger around the black hole, creating dynamic interactions with the surrounding environment. Unlike the more enigmatic and passive black holes that consume matter without leaving visible traces, SGRA offers a vivid narrative. The remnants of the explosion, shock waves, and heated gas continue to interact with the black hole, producing X-ray emissions and other signs of violent cosmic activity. These remnants provide clues about the explosive events that shaped SGRA Shrine, offering astronomers a rare glimpse into the violent origins of such black holes. Furthermore, SGRA East also serves as a window into understanding the very nature of black holes within their galactic environments. It highlights the deep interconnection between black holes, their surrounding stars, and the interstellar gas that permeates the vast expanse of space. By focusing on this particular region of the Milky Way, scientists gain crucial insights into the complex life cycles of stars and the dynamic processes that govern the universe around us. SGRA East represents far more than just a singular black hole. It encapsulates a cosmic narrative of birth, death, and rebirth, weaving these stages into the greater tapestry of the universe. SGRA East, a prominent feature located at the heart of our galaxy, is marked by the remnants of a colossal explosion, an event known as a supernova. Imagine, if you will, a massive star nearing the end of its life cycle, succumbing to the crushing weight of its own gravity. As the star collapses inward, it triggers a violent eruption, a cataclysmic explosion that not only obliterates the star itself, but scatters its outer layers across the surrounding space. What remains is a stunning, almost surreal structure that offers a haunting glimpse into the violent past of the star. The remnants of this explosive event are visible in various forms, including an expanding shell of gas that pulses with energy as it interacts with the surrounding cosmic material. This glowing shell of gas can be detected using a range of wavelengths of light, providing scientists with a vivid picture of the complex dynamic forces at play. Yet the remnants of the supernova are not merely limited to gas. They are accompanied by shock waves, waves of energy that ripple through nearby space, disturbing the very fabric of the cosmos. These shock waves continue to travel outward long after the initial explosion, creating an environment that is both turbulent and rich in stellar material. This turbulent region, full of remnants from the star's violent death, is a true testament to the destructive forces at work in the universe. The presence of dust and gas that lingers from the explosion's remnants adds an eerie element to this cosmic landscape. These particles slowly drift and mix with other elements of the cosmos, becoming part of a greater cosmic stew. This cosmic material serves as a constant reminder of the violent history that has shaped our galaxy. Over millions of years, the remnants of this catastrophic event will continue to influence the surrounding environment, an enduring legacy of destruction, but also of potential rebirth. SGRA East stands not only as a monument to death, but also to the cyclical processes of birth and rebirth that define the universe. Each feature of this region, whether the shock waves, the glowing gas, or the dust, encapsulates a story of destruction, yet also of the potential for new star formation. In this way, SGRA East offers a powerful reminder that even the most catastrophic events can pave the way for new beginnings. The impact of a single cataclysm can reshape entire regions of space, influencing the galactic environment for millions of years to come. To truly comprehend the secrets held within SGRA East, particularly its role as a satellite of the supermassive black hole at the center of our galaxy, scientists turn to the study of light, specifically its spectrum. Light is a treasure trove of information, acting like a cosmic fingerprint that can reveal a wealth of details about celestial objects. By studying the light emitted or absorbed by the region around SGRA East, astronomers can glean information about its composition, temperature, and movement. The spectrum of light reveals a detailed map of the cosmic ingredients present in this region. Each color in the spectrum corresponds to a different wavelength of light, and each wavelength tells a unique story about the object emitting it. For instance, specific patterns within the spectrum can reveal the presence of high-energy processes, pointing to the violent activities taking place in the area. As astronomers gather spectral data using powerful telescopes and complex instruments, they look for subtle shifts in the light, phenomena known as Doppler shifts. These Doppler shifts occur when an object moves relative to the observer. If SGRA East is moving toward Earth, the light waves become compressed, causing a shift toward the blue end of the spectrum. Conversely, if it is moving away, the light stretches, shifting toward the red. By analyzing these shifts, scientists can measure the speed at which SGRA East is moving, and they can also infer how much energy is being released by the black hole. In addition to these shifts, astronomers study a range of radiation, from radio waves to X-rays, that emanates from the region around SGRA East. Each type of radiation tells a different story about the high-energy processes occurring in the region. Powerful jets of matter and energy shoot out from this area, and by studying the radiation they emit, scientists can understand how matter behaves in such extreme conditions. By piecing together this spectral data, astronomers begin to form a clearer picture of SGRA East, its interactions with nearby matter, and the energy bursts it generates. These bursts of energy are not only a testament to the power of the black hole, but also a glimpse into the broader phenomena that occur near supermassive black holes, insights that unravel some of the deepest mysteries of our universe. Further still, the black hole located in the galaxy cluster 2261 BCG represents an even more extreme example of cosmic power. Nestled at the center of one of the largest known galaxy clusters, this black hole is both a symbol of timelessness and immense gravitational force. Imagine it as an immense engine of gravity, one capable of consuming anything that ventures too close: stars, gas, and even light. This process, while a cosmic catastrophe for anything caught in its grasp, is also part of a larger, ongoing cycle that has repeated itself over billions of years, far surpassing the lifespan of any single star or planet. Weighing in at a mass equivalent to billions of suns, this black hole is one of the largest known to science. Its sheer size doesn't just give it immense gravitational strength, it allows it to influence its surroundings in profound ways. As the black hole pulls in matter from its surroundings, it releases an incredible amount of energy in the form of radiation. This radiation is so intense that it can heat surrounding gas to millions of degrees, creating powerful jets that shoot out into space. These jets, which can stretch across vast distances, not only impact the environment of the galaxy cluster, but also affect the structure of the cosmic web, the very framework that holds galaxies together. The influence of this black hole extends far beyond just its immediate vicinity. It plays a key role in regulating the evolution of galaxies. By controlling the flow of gas, the black hole shapes the processes of star formation within the galaxies around it. The delicate balance between the matter being sucked into the black hole and the energy being expelled creates a dynamic ecosystem where creation and destruction coexist. This process, which has been occurring for billions of years, underscores the complexity of cosmic evolution, where the forces of gravity, radiation, and gas flow combine to shape the very structure of the universe. The black hole at the center of galaxy cluster 2261 BCG presents an awe-inspiring example of the boundless power hidden within these cosmic giants. Researchers are only beginning to uncover the depth of knowledge that can be drawn from studying such objects. This black hole holds vast potential, not just for understanding the life cycle of stars and galaxies, but for revealing the profound forces that shape the universe over colossal timescales. The mystery surrounding its behavior and influence on its surrounding environment is just the tip of the iceberg. As scientists continue to observe, they uncover more about how these celestial entities interact with the universe at large, potentially unlocking clues about the very formation of the cosmos itself. This black hole is much more than a curious astronomical feature. It is a timeless monument to the ceaseless forces of creation and destruction. Black holes like the one at the heart of 2261 BCG are constantly reshaping the universe, tearing apart old structures while giving birth to new ones. Their enigmatic power challenges our current understanding of physics and cosmology. The existence of such a black hole sparks inquiries into the fundamental nature of reality itself, forcing scientists to rethink what we know about space, time, and matter. But what happens when a black hole is missing from a region where one should be present? The absence of a black hole, especially in a cluster where one is expected to exist, raises a host of intriguing questions. It's like searching for a crucial puzzle piece that should fit perfectly, only to find it's nowhere to be found. Black holes are typically detected through their effects on nearby stars and gas, pulling them in with their immense gravitational force. So, if one is missing, it implies something has happened, something unusual, something we may not fully understand. One possibility is that the black hole has moved. Contrary to popular belief, black holes aren't stationary objects. They can gain enough momentum from interactions with other celestial bodies or from extreme events like supernova explosions to drift from their original positions. This mobility adds another layer of complexity to their nature. Another possibility is that the black hole has merged with another, forming a larger black hole. If this occurred, the newly formed black hole might not be detectable using the same methods we typically rely on for smaller black holes. And then there's the unsettling idea that the black hole may have evaporated. This concept, though based on theoretical physics, suggests that even black holes, these incredibly dense regions of space, could eventually vanish over time through a process known as Hawking radiation. According to this theory, over an unimaginably long period, a black hole could gradually lose its mass until it disappears entirely, raising yet another set of questions about the ultimate fate of such cosmic entities. Each scenario, whether it's the black hole moving, merging, or evaporating, forces scientists to reconsider the dynamic nature of these cosmic giants. The very idea that black holes could evolve in ways we haven't fully understood yet opens up a myriad of possibilities. What happens to black holes over time? How does their existence, or their potential non-existence, affect the broader structure of the universe? These questions are at the forefront of astronomical research, pushing the boundaries of human knowledge about the universe itself. At the heart of 2261 BCG lies one of the largest known black holes, possibly with a mass more than 1 billion times that of our Sun. But what makes this black hole even more fascinating is not just its size, but its behavior. Most black holes are thought to consume everything in their vicinity, siphoning off gas, dust, and even entire stars. However, the black hole at the center of 2261 BCG appears to have a unique relationship with its environment. Rather than simply devouring matter, it is believed to expel vast jets of energy and material into space. These powerful jets have the potential to shape the star formation processes within the galaxy, acting like a cosmic feedback loop. This expulsion of energy and matter raises profound questions about how black holes evolve and how they interact with their host galaxies. Rather than being isolated cosmic objects, black holes seem to be deeply intertwined with the galaxies they inhabit. This observation underscores the idea that black holes play a crucial role in cosmic ecology. They don't just consume, they create. They influence not only the immediate environment around them, but also the larger structures of the galaxy, shaping the behavior of gas clouds, impacting the formation of new stars, and possibly even influencing the very evolution of galaxies themselves. The black hole at the center of 2261 BCG is a prime example of this intricate relationship. It is a central player in the continuous dance of creation and destruction that defines the universe. Its behavior, often puzzling, invites deeper scientific inquiry and captures our imagination, compelling us to explore the vast unknowns of the cosmos. The discovery of a rapidly moving black hole such as 3C186 stirs powerful emotions and provokes existential thoughts. Imagine an object so dense that its gravitational pull is nearly immeasurable, swirling and racing through space at incredible speeds. This particular black hole is not stationary. It is in motion, speeding through the cosmos with such velocity that it seems to be tearing through everything in its path. When we think of black holes, we often envision them as cosmic vacuum cleaners, sucking in everything around them. But when a black hole is moving rapidly, it seems even more ominous. The idea of such a powerful, fast-moving object evokes visions of a catastrophic force that could unravel the delicate structure of the universe itself. The implications of such a discovery are unsettling. Black holes can warp space and time, and their unpredictability makes them feel like an uncontrollable force of chaos. If one were to approach a black hole like 3C186, the gravitational effects would be so extreme that it would tear apart anything that ventured too close in a process known as spaghettification. This dramatic imagery evokes thoughts of an apocalyptic event, an unstoppable force that leads to inevitable destruction. These terrifying thoughts challenge our understanding of the universe, making us confront the fragility of the cosmic structure and the seemingly insignificant role we play in it. Moreover, as scientists observe black holes like 3C186 moving at such incredible speeds, it forces us to reconsider the stability of the universe. The more we learn about these celestial giants, the more we realize how little we truly understand about the forces that shape the cosmos. Each discovery opens new questions, prompting us to re-examine everything we thought we knew about the universe and our place within it. When scientists detect a black hole far away from its host galaxy, it raises yet another intriguing possibility. Typically, black holes reside at the centers of galaxies, where they exert immense gravitational influence on the stars and gas within their reach. But when a black hole is found far from its expected location, it prompts scientists to ask, how did it end up there? One possibility is that the black hole was once part of a galaxy that was destroyed or altered in some way. Perhaps the galaxy merged with another, and during this collision, the black hole was ejected into intergalactic space. This scenario suggests that black holes may not only form from the collapse of massive stars, but also from complex interactions during cosmic events. The presence of a black hole far from its expected home challenges existing models about the environments where these cosmic entities arise, and it may indicate that black holes are more common than we ever imagined. This discovery could redefine how we think about the formation and distribution of these mysterious objects in the universe. The story of the black hole at the heart of 2261 BCG, along with the many other discoveries that continue to emerge, reminds us that the universe is far more complex and mysterious than we can fully comprehend. Black holes, once thought to be simple static objects, reveal themselves to be dynamic and central to the cosmic narrative. As we continue to observe and study these cosmic giants, we inch closer to unlocking the deepest secrets of the universe, while simultaneously opening up new realms of inquiry that could challenge our very understanding of space, time, and reality itself. The presence of a solitary black hole far removed from its galaxy raises profound questions about the dynamics of galaxies and the nature of the universe itself. If black holes can exist detached from their galaxies, it suggests they might influence the gravitational interactions of their surroundings in unexpected ways. Such rogue black holes could alter the movement of stars and gas in their vicinity, potentially modifying the behavior of nearby galaxies. The fact that a black hole exists so far from its original home galaxy opens a door to understanding how these cosmic giants evolve. The mystery behind its journey through space might offer clues to the underlying conditions that govern the formation and evolution of black holes, shedding light on the enigmatic forces of dark matter and dark energy. These are forces we still don't fully understand, yet they seem to permeate the universe and guide its evolution. Studying these displaced black holes could provide us with invaluable insights into the nature of gravitational waves. Gravitational waves, the ripples in space-time caused by massive cosmic collisions, offer us a way to peer into the deepest, most dynamic events in the universe. When black holes merge, the resulting gravitational waves spread across the cosmos, detectable by observatories. A black hole in an unexpected position might indicate that it was once part of such a cosmic event, offering clues about the history of black hole mergers, the forces at play, and the formation processes that give rise to these titanic structures. These observations add pieces to the ever-expanding puzzle of black hole physics, helping scientists refine our understanding of their role in galactic evolution and the broader universe. The case of 3C1886, a distant quasar, further highlights the intense complexity of the cosmic forces at play. This quasar is powered by a supermassive black hole that is consuming material from its surroundings at an astonishing rate. The energy released during this process is so immense that it outshines entire galaxies, lighting up vast regions of space with an intensity that can distort the very fabric of space-time. As matter spirals into the black hole, it doesn't simply vanish. Instead, it creates powerful jets of energy that shoot out into space, traveling at speeds fast enough to bend the space around them. These jets are not harmless streams of gas. They can have profound effects on surrounding galaxies, potentially disrupting their structure and star formation. 3C 1886's journey through space is not just an isolated event. It is part of a larger cosmic story, shaped by the gravitational pull of nearby objects and interactions with other celestial phenomena. If this quasar were to collide with another galaxy, the consequences could be dramatic. The collision might trigger a burst of star formation, or it could unleash gravitational turbulence that disturbs the orbits of nearby stars and planets, causing ripples of cosmic chaos. For scientists, these scenarios illustrate the delicate balance between the grandeur and chaos of the universe, underscoring the fact that even in the vastness of space, the forces at play are often unpredictable and profound. Every observation of 3C 1886 adds new layers to our understanding of black holes and their immense role in the evolution of galaxies. These titanic forces, which can alter the course of galaxies and shape the very fabric of space-time, remind us of the interconnectedness of the cosmos. The behavior of such celestial objects calls into question our assumptions about the stability and predictability of the universe. The very notion of a cosmic order, so often thought to be fixed and immutable, is constantly challenged by the unpredictability of black holes and their interactions. Meanwhile, the mystery of the missing black hole in the galaxy cluster Abell 2261 presents another layer of intrigue, one that borders on cosmic horror. Astronomers have long expected to find a supermassive black hole at the center of the largest galaxy in this cluster. This black hole would typically serve as the gravitational anchor for the surrounding stars and gas, influencing their motions and helping to define the galaxy's structure. However, in Abell 2261, this expected black hole is conspicuously absent, creating an eerie void in the heart of the galaxy where one should be. This absence raises unsettling questions. Where did the black hole go? Black holes generally grow by consuming material from their surroundings, so its disappearance suggests something truly extraordinary may have occurred. One possibility is that the black hole merged with another, but this raises even more disturbing questions. Such mergers typically produce massive gravitational waves, sending ripples through the fabric of space-time that could be detectable across vast distances. Yet, there is no sign of these waves emanating from the cluster. Another theory is that the black hole is hiding, obscured from our detection methods in ways we can't yet comprehend. Imagine a massive gravitational force lingering in the shadows, influencing the entire galaxy without leaving a single detectable trace. This idea taps into a deep sense of cosmic unease, evoking the fear of a force that exists but remains beyond our understanding. It's as if something vital is hidden just beyond our reach, waiting to be uncovered. This mystery goes beyond one isolated galaxy. It speaks to the larger, ongoing puzzle of the universe's hidden secrets. It serves as a reminder that no matter how much we learn, there may always be aspects of the cosmos that remain elusive, unknowable, and perhaps even unknowable for all time. The absence of a black hole in Abell 2261 reminds us how much remains hidden in the vast, ever-expanding universe, like phantoms in the dark. It's a haunting reminder that, even in the midst of our most advanced explorations, there may be cosmic forces that defy our comprehension. The very existence of black holes challenges our fundamental understanding of the universe. These enigmatic objects are regions of space where gravity is so intense that not even light can escape. They represent a fundamental disruption to the hierarchy of celestial bodies, where stars and planets are typically the dominant players. A black hole, in contrast, is like a cosmic wildcard, a force of destruction that can consume entire stars, reshape galaxies, and create chaotic environments where the rules of the universe as we know them no longer apply. Imagine a predator in the vast, dark expanse of space, capable of devouring entire systems of matter and rewriting the very fabric of space-time itself. This unpredictability shakes our understanding of the universe to its core. When something as stable as matter can be torn apart by the immense gravity of a black hole, it forces us to confront the fragility of cosmic structures. The sense of order that humans often project onto the universe, seeing it as a reliable, predictable system, is quickly undermined by the reality of black holes. The presence of black holes forces us to ask deep, existential questions about our place in the cosmos. If the universe can be transformed by forces so mysterious and powerful, what does that say about our understanding of existence itself? As researchers continue to probe these enigmatic objects, it becomes clear that the universe is far more complex and unpredictable than we could ever have imagined. Black holes are not just cosmic phenomena. They are symbols of the unknown, forces of nature that defy our attempts to categorize them neatly. They inspire awe, evoke terror, and in many ways represent the ultimate reminder of how much we have yet to learn about the universe. Looking forward, as we continue to explore the cosmos, particularly the areas where the most extreme phenomena occur, such as regions filled with aging star systems or areas where black holes consume everything around them, we are likely to uncover new truths that will radically reshape our understanding of the universe. Advanced telescopes and technologies may allow us to observe phenomena that challenge long-held assumptions about cosmic evolution, such as the idea that galaxies are constantly producing new stars. Instead, we may find that many galaxies are in a state of slow decline, their vibrant star-forming days behind them, fading into darkness. Such a realization would upend our optimistic view of the universe as an ever-evolving dynamic system, forcing us to reconsider the future of the cosmos and our place within it. As we delve deeper into the remnants of supernovae, we may uncover profound insights about the violent, explosive deaths of stars and the crucial role they play in the cosmic recycling of elements. Every star that reaches the end of its life cycle and explodes in a supernova leaves behind a legacy, a cloud of matter and energy that, over time, spreads throughout the universe. This stellar material, rich with elements forged in the star's heart, can eventually form new stars, planets, and even life. Understanding these explosive events could unlock a clearer picture of how the universe constantly renews itself, despite its chaotic nature. However, the more we learn about these cataclysmic deaths, the more we may come face to face with grim realities about the fragility of life in the cosmos. It's easy to think of the universe as teeming with life, but in reality, only a small fraction of stars have the right conditions to foster planets that could support life. This realization invites us to reconsider our place in the universe, emphasizing how rare and delicate the conditions for life truly are. In addition, exploring regions of space densely populated with dark matter might reveal unexpected ways this invisible substance shapes the formation of cosmic structures. Dark matter, which makes up a significant portion of the universe's mass, does not emit light or interact with electromagnetic radiation, making it difficult to study. However, its gravitational influence is undeniable. It's believed to play a crucial role in the formation of galaxies, clusters of galaxies, and other large-scale structures in the universe. As we study these dark matter-rich regions, we may discover how it bends and warps space-time, and perhaps even how it creates environments hostile to life. Could the gravitational forces of dark matter prevent life from emerging in some areas, making the story of life in the universe even more complex than we ever imagined? Our exploration of these far-reaching regions may lead us to unsettling truths about the delicate balance between creation and destruction. The universe is a place of both stunning beauty and harsh realities, where birth and death are inextricably intertwined. These observations could dramatically shift our perception, reminding us that the cosmos is not solely a realm of wonder and growth, but also a vast, often inhospitable space shaped by forces far beyond our understanding. Among the many objects that reveal the universe's enigmatic nature, Cygnus X1 stands out as one of the most remarkable. This binary star system, located millions of light years from Earth, hosts a supermassive black hole that is devouring material from its companion star. As gas and dust spiral into the black hole, they are heated to unimaginably high temperatures, generating intense radiation across various wavelengths, X-rays, gamma rays, and more. Within this turbulent environment, the radiation creates a region so hostile it can only be described as a nightmarish zone, one where the usual processes of stellar birth are thwarted. The extreme radiation from Cygnus X1 is not just a minor inconvenience for the gas clouds and atoms in its vicinity. It has the power to strip away their outer layers, ionize atoms, and drastically alter the chemistry of the region. This disruption prevents the usual dance of stellar birth, effectively sterilizing large portions of the galaxy. Instead of being a place where new stars might emerge, Cygnus X1's environment is a harsh, radiation-saturated expanse where life, if it ever existed, would stand no chance. The extreme forces at play in this system reveal the profound impact that supermassive black holes can have on their surroundings, preventing the formation of vibrant stellar landscapes and altering the very fabric of their cosmic neighborhood. The force exerted by the black hole in Cygnus X1 is unlike anything we experience in our own solar system. Its gravitational pull is so strong that nearby stars and any planets within the system are affected by its immense gravity. As these stars approach the black hole, they may find themselves caught in its gravitational grip, spiraling inward over time. As they get closer, they are subjected to extreme tidal forces that distort and stretch them, and in some cases, they may be torn apart and consumed by the black hole. The energy released during such an event is staggering, creating a burst of radiation that can be observed across vast distances in space. If any planets orbiting stars near Cygnus X1 find themselves too close to this cosmic giant, their fate is equally precarious. The intense gravitational forces may pull them from their orbits, sending them careening through space. Some may collide with other celestial bodies, while others could be flung from their home star system entirely. The radiation and high-energy particles produced by the black hole would also pose a serious threat to any potential life forms, rendering survival nearly impossible. In the shadow of Cygnus X1, any worlds that might exist are subjected to a relentless and unyielding force that alters the very nature of their existence. The dynamics of Cygnus X1 illustrate the powerful and sometimes violent nature of cosmic interactions. It serves as a stark reminder of how the forces at play in the universe are not just beautiful and awe-inspiring. They are often chaotic and destructive, reshaping entire star systems and planetary environments in the blink of an eye. One of the most fascinating aspects of astrophysics lies in the study of binary black hole systems. These systems, where two black holes orbit each other, create an extraordinary environment that offers a natural laboratory for studying the extremes of physics. As the black holes spin and interact, they produce gravitational waves, ripples in space-time itself. When two black holes merge, the energy released is equivalent to the energy produced by millions of supernovae, sending out shockwaves that can be detected across vast distances. These gravitational waves offer scientists a new way to study black holes in ways that were previously impossible. By analyzing the frequency, amplitude, and other characteristics of these waves, scientists can learn about the masses, spins, and formation processes of black holes. These observations are helping us better understand not only black holes, but also the very fabric of space-time itself. Gravitational wave astronomy is opening a new frontier in our quest to comprehend the fundamental laws of the universe, offering insights into some of the most extreme and mysterious phenomena known to science. The area surrounding a black hole is one of the most extreme and hostile environments in the cosmos, characterized by forces and phenomena that stretch the very limits of our understanding of physics. Here, gravitational forces are so intense that they warp the fabric of space itself, while powerful magnetic fields intensify the region's hostile nature. This high-energy zone becomes particularly active when matter begins to fall into the black hole, forming an accretion disk, a swirling, luminous mass of gas and dust. As this matter spirals inward, it is subject to immense friction, causing it to heat up to temperatures that are nothing short of staggering. This process generates vast amounts of energy, primarily in the form of radiation that spans the electromagnetic spectrum, from X-rays to gamma rays. As a result, these systems are among the brightest objects in the universe, often outshining entire galaxies. By studying this high-energy radiation, Astrophysicists are able to peer into the behavior of matter in conditions far beyond what we experience on Earth. The extreme environments surrounding black holes present an invaluable opportunity to test the limits of physics, particularly in terms of how gravity interacts with the other fundamental forces of nature. It is in these regions that we observe strange and often mind-bending phenomena, such as time dilation, the stretching or compression of time as we approach the event horizon, and the bizarre behavior of matter, which seems to defy the usual laws of physics. These unusual observations challenge our current understanding of the universe, offering clues about the potential intersection of gravity and quantum mechanics, a realm where classical physics breaks down and new theories may emerge. In essence, black hole systems serve as natural laboratories of the cosmos, places where we can explore the most extreme behaviors of matter and energy. They provide a testing ground for new ideas and hypotheses, pushing the boundaries of what we know and fueling curiosity. As scientists continue to observe and study these celestial giants, they stand on the cusp of discovering new aspects of physics that could ultimately reshape our understanding of the universe. By delving deeper into the mysteries of black holes, researchers aim to refine existing theories and uncover new ones, bringing us closer to answering some of the most profound questions about the nature of reality. Among the vast array of black holes scattered across the universe, the supermassive black hole at the center of NGC 4889 stands out as an extraordinary giant. It is one of the largest known black holes, with a mass estimated to be approximately 24 billion times that of our Sun. To truly grasp the scale of this behemoth, imagine the Sun as a soccer ball. Now, picture a massive mountain looming over it. That's the relative size of the black hole in NGC 4889 compared to our own star. Such an immense object stretches the limits of our theoretical models and forces us to reconsider how such massive black holes come into existence. How can something so large form in a universe where even other supermassive black holes, though smaller, are already awe-inspiring? The presence of NGC 4889 challenges our understanding of cosmic evolution, offering a window into the mystery of how galaxies and their central black holes evolve over time. The sheer scale of NGC 4889 and the implications of its existence raise intriguing questions about the dynamics of galaxies and the forces that govern their formation and evolution. How do these titanic black holes influence the galaxies around them? What does their massive gravitational pull mean for the surrounding stars, gas, and dark matter that populate their environments? These questions fuel the curiosity of astronomers, who continue to study black holes in an effort to unravel the mysteries of the cosmos. The discovery of such massive objects serves as a reminder of the incredible diversity of structures in the universe, as well as the vast array of phenomena that remain hidden from our view, waiting to be understood. At the heart of every galaxy, black holes, despite their apparent dormancy, pose an ever-present threat due to their immense gravitational influence. The life cycle of a black hole is marked by periods of activity and dormancy, depending on whether it is actively consuming nearby gas and stars. When a black hole is feeding, it behaves like a cosmic vacuum cleaner, pulling in everything in its path. But during quieter periods, when it is not accreting any matter, it can lie dormant for vast stretches of time, silently lurking in the dark recesses of space. This absence of activity, however, does not mean the black hole is powerless. Rather, it exists in a state of delicate equilibrium, awaiting the next chance to spring back to life. The immense size and gravitational pull of a black hole mean that it can affect its surroundings even without actively consuming matter. For instance, the warping of space around a black hole can alter the orbits of nearby stars, causing them to shift in ways that would otherwise be impossible under normal circumstances. These gravitational forces extend over vast distances and can influence the entire galaxy in which the black hole resides. In this way, even when dormant, black holes remain active players in their cosmic neighborhoods, guiding the motion of celestial bodies and ensuring their lasting presence as cosmic giants. In fact, black holes have outlasted many of the most dramatic and violent events in the universe's history. Their incredible density and gravitational strength make them incredibly resilient to external forces. Stellar explosions, the collapse of entire star systems, and even the violent collisions between galaxies. Each of these events has occurred throughout the history of the cosmos, but black holes have endured. These titans of gravity have withstood the tremendous pressures of explosive stellar deaths and the cataclysmic forces of galactic mergers. Each of these events adds another layer of complexity to the already multifaceted nature of black holes, solidifying their role as the guardians of cosmic balance. However, it is the apparent silence of black holes during their dormant periods that presents one of the most haunting aspects of their existence. While they may appear at rest, this silence belies the underlying threat they pose. Their potential for destruction remains ever present, reminding us that danger can often lie in the quietest of places. This eerie calm is not a sign of weakness, but rather a testament to the delicate balance of cosmic forces that govern their behavior. Black holes, even when hidden away in the shadows of space, continue to exert influence on their surroundings, shaping the structure and evolution of entire galaxies. Their presence is a constant reminder of the intricate and dynamic relationships that define the universe. The black hole at the center of NGC 4889 exemplifies this silent power. Though it may remain invisible for long stretches of time, its gravitational pull shapes the galaxy in profound ways. Like an unseen predator, it waits in the background, exerting influence over the stars and gas in its vicinity. The black hole's gravitational force is so powerful that it can alter the orbits of stars, drawing them closer to the event horizon, where they will eventually be consumed. This gravitational dance can take millions of years to unfold, emphasizing the long-term, often unnoticed impact black holes have on their host galaxies. Thus, black holes remain one of the most mysterious and awe-inspiring phenomena in the universe. Silent yet ever-present, they shape the cosmos in ways that are still only partially understood. As scientists continue to study these cosmic giants, they hope to unravel the many mysteries that black holes present, learning more about the nature of space, time, and gravity in the process. In the case of NGC 4889, this supermassive black hole stands as a reminder of the vast scale of the universe and the incredible forces that govern it, challenging our theories and pushing us ever closer to understanding the ultimate nature of reality itself. The growth of supermassive black holes, while seemingly slow, is often a quiet, almost imperceptible process, unfolding over vast spans of time. These cosmic giants typically grow by accumulating matter from their surroundings. Stars, gas, and dust spiral inward, drawn inexorably by the black hole's powerful gravity. Over the course of millions or even billions of years, this process continues, feeding the black hole, yet often hidden from our observation. It is only when dramatic cosmic events occur, such as a star's sudden explosion near the black hole, that the gradual accumulation of matter becomes apparent. In the context of galactic dynamics, NGC 4889 provides a perfect example of how supermassive black holes can exert both tremendous power and elude detection. The galaxy itself may undergo significant evolution, with stars being born and dying, while at the center, the black hole remains a silent, unseen force. Its gravitational influence is profound, subtly guiding the motion of stars and the gas within the galaxy. The black hole's ability to consume matter and shape galactic dynamics is a constant, though often invisible, presence. Over the eons, it quietly alters the balance of the galaxy, shaping its future in ways that are not immediately apparent to the casual observer. In stark contrast, the supermassive black hole at the heart of the Phoenix cluster is an example of a black hole that is anything but quiet. This black hole is an active and powerful entity, exerting an extraordinary amount of energy into its surroundings. Unlike more passive black holes, it produces immense energy, including powerful jets of particles that are shot out at nearly the speed of light. These jets release energy millions of times greater than that emitted by our sun, extending their reach across vast distances in space. The energy from these jets can profoundly affect the surrounding gas, heating it to temperatures so high that it emits a blinding glow of X-rays. These high-energy emissions serve as crucial clues for astronomers, allowing them to study the black hole's behavior and influence on its environment. As the black hole pulls in gas and dust from the surrounding cluster, the material heats up to extreme temperatures. This process produces X-rays that are detectable by space telescopes, offering a window into the black hole's ferocious appetite. The gravitational forces at play are not only evident in the intense heating of material, but they also create ripples in the fabric of space-time itself. These ripples, or gravitational waves, ripple outward from the black hole, altering the motion of nearby stars and galaxies. The black hole's presence, though unseen, fundamentally alters the structure of its galaxy and the larger cluster it resides in. The energy outputs from the Phoenix cluster black hole demonstrate the overwhelming power that black holes can exert on their environments. These immense energy emissions are not just a byproduct of the black hole's activity. They actively shape the gas and dust in their surroundings. In some cases, the energy from the black hole can prevent the gas from cooling down and condensing into new stars. In this way, the black hole can stifle the birth of new stars, potentially affecting the entire evolution of the galaxy cluster. It shows that black holes are not just passive observers of the cosmos, but active participants, shaping the future of their cosmic neighborhoods. Moreover, the gravitational pull of a supermassive black hole impacts the orbits of stars throughout the galaxy and beyond, creating a complex dance of motion and interaction. As galaxies collide and merge, the influence of the central black hole can intensify, sometimes leading to the merging of smaller black holes into a larger, more powerful one. This growing strength of the central black hole further asserts its dominance, not just over its host galaxy, but over the entire cluster of galaxies. In this way, black holes establish a terrifying hierarchy, with their gravitational influence dictating the fate of their surroundings. Their unseen but palpable presence shapes the very fabric of cosmic existence. In the wider universe, radio emissions from distant cosmic entities such as pulsars, quasars, and particularly powerful galaxies serve as cosmic beacons of energy. These emissions are like ripples that propagate across the vast stretches of space, interacting with the intergalactic medium, the relatively empty space between galaxies filled with gas, dust, and energetic particles. These radio waves, as they travel across space, have the ability to interact with the diffuse gas, subtly altering its temperature and electromagnetic properties. Even small shifts in temperature can have a profound impact, especially in the cold, nearly empty reaches of the universe. This seemingly insignificant warming can influence the behavior of gas flows and star formation, impacting the development of galaxies over enormous distances. The impact of radio emissions can also be seen in the cosmic microwave background radiation, a remnant of the early universe. These emissions contribute to the background radiation that permeates all of space, providing crucial insights into the conditions of the early universe. Furthermore, as radio waves interact with the gas, they can ionize neutral hydrogen and other elements in space, creating regions of ionized plasma. This plasma, in turn, interacts with magnetic fields, creating intricate structures that can stretch across light years. These radio waves, with their immense energy, cast long shadows across the universe, reminding us that even in the emptiness of space, the echoes of energetic events can influence everything from the composition of the intergalactic medium to the future evolution of galaxies. One of the most famous cosmic sources of X-rays, Cygnus X1, began as an enigma, one of many points of light detected in the sky. These high-energy X-rays hinted at the presence of an extraordinary object, but it wasn't until the early 1960s that astronomers recognized the significance of this source. Located in the constellation Cygnus, Cygnus X1 was initially thought to be just a random flare of energy. However, as scientists studied the X-rays in greater detail, they realized that the source was not a singular event, but part of a binary system, two stars locked in a gravitational dance. One of these stars was a blue supergiant, a massive star nearing the end of its life. The other, the unseen companion at the heart of the X-ray emissions, was a black hole. The black hole was drawing matter from the supergiant, creating an accretion disk, a swirling disk of gas being pulled toward the event horizon. As astronomers observed the motions of the visible star and its unseen companion, they noticed that the gravitational forces at play were far greater than those of any normal star. This led to the realization that the invisible object was a black hole, its immense density so great that not even light could escape its grasp. The discovery of Cygnus X1 was groundbreaking. It became the first strong candidate for a black hole, offering scientists a rare glimpse into the extreme conditions surrounding such an enigmatic object. The study of this binary system allowed astronomers to better understand the nature of black holes, shaping our understanding of these cosmic entities and their role in the universe. Cygnus X1's story transformed from an unknown X-ray source into a pivotal moment in the history of astrophysics. The system of Cygnus X1 continues to fascinate astronomers and the public alike. It serves as a striking example of the raw power and mystery of black holes. At the heart of the system, the black hole exerts an immense gravitational pull, distorting the fabric of space-time itself. The force of this pull is so strong that it raises profound questions about the nature of existence, the limits of human understanding, and our place in the cosmos. To contemplate the edges of a black hole where not even light can escape is to reflect on the fragility of life itself. In the face of such immense power, one cannot help but be reminded of how small and insignificant we are in the grand tapestry of the universe, underscoring the vastness of the cosmos and the limits of human knowledge. The concept of time, an ever-present force in our daily lives, behaves in strange and paradoxical ways when it comes into proximity with black holes, adding unsettling layers to our deepest fears. Time, as we know it, slows down dramatically near such a massive object. Observers far away from the black hole would witness events unfolding in a rapid, almost chaotic manner, while those closer to the black hole would experience a completely different reality, one where time seems to stretch endlessly. This stark disparity between the experience of those near the black hole and those at a distance compels us to reflect on the very nature of reality itself. It introduces a sense of uncertainty and disorientation regarding our own future, a future that could be shaped by forces beyond our comprehension. The idea of being drawn into a black hole resonates with existential dread. It symbolizes not just an end, but the ultimate point of no return. Once inside, there would be no escape, no possibility of survival, no way to avoid being consumed by the black hole's infinite pull. This singularity, this bottomless abyss, could swallow all that we are and all that we know, leading us into a void of obscurity. Such a scenario forces us to reflect deeply on the nature of our mortality and the fleeting nature of human achievement. It stirs within us a sense of urgency, a desperate push to explore the universe, to learn and to grow, while we still have the time, before we too are consumed by the unknown. Further adding to the sense of awe and fear is the spectacle of cosmic systems like the one at the heart of Cygnus X1. As we peer into this distant realm, we encounter an unpredictable dance of celestial forces, reinforcing the understanding that the universe is full of mysteries, many of which remain beyond human control or understanding. The chaotic interactions we observe in systems like Cygnus X1 highlight our insignificance in the grand cosmic scheme, a reminder of our inability to fully comprehend the forces that govern everything around us. This realization, in turn, breeds existential anxiety, as it lays bare the limits of human knowledge and the precariousness of our existence. Cygnus X1 is a particularly captivating celestial object that has intrigued astronomers and physicists for decades. What makes it so fascinating is its unique interplay between light and shadow, a dynamic that reveals much about the violent nature of black holes. At the very heart of Cygnus X1 is an intense and powerful source of X-rays, a signature of the violent activity taking place as it engages in a dramatic and destructive dance with its companion star. The black hole itself is invisible, yet it exerts an enormous gravitational pull on the nearby star, siphoning off material from it. This material spirals toward the black hole in a process known as accretion. As it heats up, it forms a brilliant disk of hot, glowing gas that emits X-rays detectable by our telescopes. The contrast between this bright, radiant gas and the inky darkness of the black hole itself creates a visual metaphor for both destruction and creation, as light is born from the edge of oblivion, only to be swallowed whole by the black hole's inescapable grasp. The more scientists study Cygnus X1, the more they uncover about its behavior, revealing the complexities of black hole dynamics. By observing fluctuations in the brightness of the X-ray emissions, researchers can infer how active the black hole is and how quickly it is consuming its companion star. These dynamic changes offer valuable insights into the extreme conditions of black holes, shedding light on the intricate physics at play in these cosmic environments. As scientists continue to study Cygnus X1, they gain a deeper understanding of how black holes influence the space around them, not only consuming matter, but also warping and distorting space-time itself. Cygnus X1 is also notable for its place in the history of astronomy. It was one of the first objects to be strongly considered as a potential black hole, marking a turning point in our understanding of these mysterious cosmic objects. This historical significance adds another layer to its intrigue, as researchers revisit it not only to study the ongoing phenomena within the system, but also to appreciate how far our understanding of the universe has come over the years. With each new technological advancement, our ability to observe and analyze these complex systems grows, ensuring that Cygnus X1 will continue to be a focal point for astronomers eager to unravel the mysteries of the cosmos. In a similar vein, gravitational lensing is another fascinating phenomenon that reveals the power and influence of black holes. Gravitational lensing occurs when massive objects, like black holes, warp the fabric of space-time around them. This bending of light is most dramatically observed in systems like Max J 11149 plus 223, a galaxy cluster that contains a supermassive black hole. The black hole bends the light from objects behind it, much like a heavy ball placed on a stretched-out fabric causes nearby objects to curve. By studying the way this distortion affects the light from distant galaxies, astronomers can gather valuable clues about the hidden nature of the light itself, revealing details about the galaxy's structure and, more importantly, the mass and gravitational pull of the black hole. The light that is magnified and stretched into arcs around the black hole provides scientists with a rare opportunity to study objects that would otherwise be too faint or too distant to detect. This gravitational lensing effect not only helps us learn more about the distribution of mass in the galaxy cluster, but also unveils the unseen horrors of the black hole itself. By analyzing the way light bends, scientists can deduce vital information about the black hole's mass and gravitational strength. This information is crucial for understanding the black hole's influence on its environment and the extreme conditions surrounding it. Regions near the black hole are filled with powerful radiation and chaotic dynamics, offering a glimpse into the destructive forces at play just outside the event horizon. Thus, the lensing effect in Max J 1149 plus 223 does more than just visually demonstrate the presence of a black hole. It reveals the terrifying reality of the cosmic forces at work, showing how these forces interact with light and matter in profound and often violent ways. It offers a rare insight into the mysteries that swirl around these cosmic giants, which continue to lurk in the depths of the universe, largely out of reach of human understanding. The discovery of black holes, especially those formed in the early universe, provides profound insights into the origins and evolution of the cosmos. These ancient black holes act as time capsules, preserving information about the conditions of the universe just moments after the Big Bang. By studying these primordial black holes, scientists can gain a deeper understanding of how galaxies and large-scale cosmic structures began to take shape. The growth patterns of these black holes also provide clues about the mysterious nature of dark matter, an invisible substance that plays a critical role in shaping the universe. As our understanding of black holes and their role in the cosmos continues to evolve, it challenges our previous conceptions of these objects. Once viewed primarily as destructive forces, black holes are now recognized as key players in the cosmic drama, revealing secrets about the early universe and offering a glimpse into the nature of dark matter and the forces that govern the entire universe. They may not just be agents of terror, they may hold the key to understanding the very fabric of reality itself. Through the lens of modern science, black holes have transitioned from being mere cosmic predators, feared for their insatiable appetite for matter, into complex entities that serve as the very architects of the universe. This shift in perception has profound implications for how we understand both the terror and awe these cosmic giants evoke. No longer just the harbingers of destruction, Black holes have emerged as something far more profound, inviting us to examine them not only through the lens of fear, but also of fascination. Their gravitational pull, which once seemed like a mindless force of annihilation, now appears as a critical engine driving the evolution of the cosmos. This duality forces us to reconsider how we perceive the very nature of existence, as it suggests that black holes are not just destroyers, but builders, crafting the universe in ways we are only beginning to understand. As our knowledge deepens, it becomes increasingly clear that black holes are fundamental to the birth and shaping of the universe itself. Rather than standing as isolated and terrifying anomalies, they are crucial pieces of the cosmic puzzle, fundamental to our understanding of the very forces that govern space and time. This realization not only redefines black holes as objects of intrigue and importance, but suggests they may hold the answers to some of the most profound questions of existence. In this sense, they are not merely objects of cosmic terror, but also of scientific wonder. The key to unlocking the mysteries of everything from the origins of the universe to the nature of dark matter and dark energy. Imagine, if you will, each black hole as a gateway, a portal to understanding the fundamentals that underpin the universe. These colossal structures are not only gravitational juggernauts, swallowing stars and gas with insatiable voracity, but they challenge our current theories about the nature of the cosmos itself. They force us to rethink our understanding of space, time, and gravity. Every new observation brings with it the potential to rewrite the rules of physics. As astronomers and physicists gather increasingly sophisticated data from advanced telescopes and space missions, they are beginning to uncover features of black holes that challenge our conventional understanding of the universe. This data could illuminate previously unexplored regions of space, offering insights into how these gravitational giants distort the fabric of space-time and interact with their environment. One area where black holes are particularly revealing is the way they influence the behavior of nearby stars. By studying the motion of stars near these cosmic behemoths, scientists can deduce how powerful gravitational fields warp the surrounding space-time, offering crucial information about the nature of gravity and the structure of space-time itself. These observations can also shed light on how stars form and evolve in environments where gravity is far more intense than we experience in the relatively tame conditions of Earth's solar system. Furthermore, when black holes interact with one another, they could offer a rare glimpse into how gravitational forces link together with other fundamental forces like electromagnetism, forces that govern the very building blocks of the universe. Such interactions could lead to a profound reevaluation of how these forces interact, offering scientists the potential to develop a unified theory that merges gravity with the other three fundamental forces. This could help answer deep existential questions about how the universe began, how it may end, and the roles these enigmatic objects play in the cosmic life cycle. As scientists press on with their work, their discoveries might also bring us closer to understanding some of the universe's most elusive components, dark matter and dark energy, mysterious forces believed to make up the majority of the universe's mass, yet largely invisible to our current methods of observation. Black holes, with all their awe-inspiring power, may hold the answers to unlocking the true nature of these dark forces. By studying the ways in which they influence the matter around them, how they bend light, how they distort the trajectories of stars, how they trigger the creation of new cosmic structures, scientists may gradually unravel the secrets of these unseen forces. Each new breakthrough, no matter how incremental, pushes the boundary of human knowledge further, bringing us closer to answering questions that have persisted for millennia. These discoveries are not just about understanding how the universe functions. They may one day help us understand why it exists at all. One particularly intriguing puzzle is the black hole believed to reside at the heart of the dwarf galaxy Leo 1. Dwarf galaxies like Leo 1 are typically small, faint, and far less massive than their larger counterparts, making them incredibly difficult to study. Leo 1 is located at a significant distance from Earth, and though evidence suggests a black hole lies at its core, proving its existence remains elusive. What adds to the mystery is the potential size of the black hole. If it exists, it may be far smaller than the supermassive black holes typically found at the centers of larger galaxies. Instead, it may resemble the smaller black holes formed by the collapse of massive stars. The challenge for astronomers is understanding how such a black hole could have formed in a galaxy that contains so few stars. To detect its gravitational influence, scientists are relying on advanced observational techniques to analyze the motion of stars in Leo 1. The way these stars move, the speed at which they orbit, and the paths they trace across the galaxy can reveal the amount of mass concentrated at the center. However, because of the galaxy's faint nature, these measurements are difficult to obtain. Yet, as observational technology continues to improve, researchers are now able to probe deeper into the galaxy, hoping to uncover the hidden black hole at its heart. If confirmed, the discovery of this black hole would not only reshape our understanding of black holes in general, but would also provide valuable insight into the nature of dwarf galaxies and the role they play in the larger cosmic ecosystem. Dwarf galaxies, once thought to be simple, stable systems, could reveal a much more complex and dynamic picture of how galaxies evolve. Their behavior, interactions, and the presence of black holes may point to deeper connections within the universe that have previously gone unnoticed. The existence of a supermassive black hole within such a small galaxy challenges long-standing assumptions about the formation and nature of galaxies. Traditionally, scientists believed that large black holes only existed at the centers of massive galaxies. The discovery of such a powerful object within a tiny galaxy upends that narrative, much like a tiny village unexpectedly discovering a massive skyscraper appearing in its midst. This discovery forces us to reconsider the very mechanics of galaxy formation, suggesting that even the smallest galaxies can harbor the remnants of explosive cosmic events. Such revelations open new doors to understanding the evolution of matter in the universe. The mere presence of a black hole within a dwarf galaxy raises questions about the conditions under which these cosmic giants form and evolve. It suggests that black holes may have been crucial players in the early history of the universe, even in galaxies that seem simple or insignificant. Moreover, this finding challenges scientists to reconsider how black holes interact with their environment. How do these dark entities affect the star formation process? Do they exert gravitational forces that influence the overall dynamics of the galaxy, or do they act as catalysts for change, driving the formation of new cosmic structures? This discovery of a massive black hole in such an unexpected place also hints at a more interconnected universe than we previously thought. If dwarf galaxies, those often overlooked by astronomers, can harbor black holes, then perhaps the dynamics of gravity and cosmic evolution are more universal and far-reaching than we imagined. The study of these black holes in miniature galaxies may reveal the complexity and diversity of the universe in ways that could force us to rethink the very foundation of our knowledge. The implications of this discovery stretch beyond the boundaries of a single galaxy. They have the potential to reshape how we view the behavior of galaxies across the cosmos, forcing us to reconsider the way we perceive the evolution and structure of the universe. What was once a mystery hidden deep within the heart of a tiny galaxy may soon become a key piece of the puzzle that unlocks our understanding of the larger cosmic picture. With each new discovery, the black hole at the center of Leo 1 offers clues that could finally reveal some of the universe's most deeply hidden secrets, pushing the boundaries of our knowledge and challenging us to reimagine what we know about the cosmos. Looking deeper into the characteristics of Leo DF's black hole provides an opportunity to unravel the mysteries of black holes themselves. Investigating its unique features, such as its size, rotation, and energy output, could radically challenge existing theories about the formation and evolution of these enigmatic cosmic objects. Such discoveries might compel scientists to rethink how black holes grow, how they interact with their surroundings, and how they influence the larger structure of the universe. Through a closer examination of this black hole, we don't just learn about one isolated phenomenon, but also gain insight into the fundamental forces and materials that govern the universe, peeling back layers to reveal its most profound and secretive workings. At the heart of this cosmic exploration is the black hole at the center of Messier 87, a galaxy located some 53 million light-years from Earth. This black hole offers a fascinating and incredibly complex case study that challenges our current understanding of how supermassive black holes evolve and interact with their environments. The black hole in Messier 87 is a true giant, possessing a mass that is billions of times that of our Sun. Its gravitational pull is so intense that it exerts an extraordinary influence on everything around it. This immense force shapes the very fabric of space, bending it in ways that defy simple explanation. Historically, scientists believed that supermassive black holes grew primarily by pulling in surrounding gas and dust, slowly accumulating mass over vast stretches of time. However, recent observations of Messier 87's black hole have forced researchers to reconsider this notion. The black hole in Messier 87 doesn't simply act as a passive consumer of cosmic material. Instead, it plays an active and dynamic role in shaping the entire galaxy. One of the most striking features of this black hole is the extraordinary jets of energy and matter that erupt from its core. These powerful jets extend far into space, stretching across vast distances, and have a profound impact on their surroundings. They do more than just push back against the material around them. They can also influence the formation of new stars within the galaxy. This active feedback loop is unlike anything previously expected. Rather than passively accumulating mass, the black hole actively reshapes its environment, sometimes even stunting the growth of nearby stars and galaxies. It creates an interconnected cycle of feeding and influencing, a kind of cosmic tug-of-war that affects the evolution of galaxies on a grand scale. This dynamic interaction calls into question our long-standing assumptions about the relationships between black holes and the galaxies they reside in. It suggests that the role of black holes may be far more complex and interactive than previously thought. Further insights into the nature of this black hole have come from the image captured by the Event Horizon Telescope, which has allowed scientists to observe the behavior of matter as it spirals into the black hole. This infalling material, subject to extreme gravitational forces, undergoes dramatic transformations that can alter the characteristics of the black hole itself. Such observations lead to hypotheses about the mechanisms behind the growth of black holes, the feeding processes that occur at their cores, and the shifts in energy states that influence their behavior. These findings challenge traditional perceptions, suggesting that supermassive black holes are not just passive entities slowly feeding over time. Instead, they appear to engage in an active and complex interaction with their cosmic neighborhoods, playing a critical role in transforming their host galaxies in profound and intricate ways. The study of Messier 87's black hole raises questions that extend far beyond the black hole itself, prompting us to reconsider our understanding of the universe as a whole. Messier 87 is home to one of the most mysterious and powerful phenomena known to science, a supermassive black hole. This object resides at the center of a galaxy teeming with swirling material that is heated to extreme temperatures. This heat creates a glowing disk of matter known as an accretion disk, a characteristic feature of many black holes. As material spirals into the black hole, it accelerates and emits intense energy, resulting in the brightest region of the galaxy. The energy released by this process is so powerful that it can outshine all the stars in the galaxy combined. Beyond the accretion disk, a remarkable feature of the black hole is the presence of powerful jets of particles that are expelled at nearly the speed of light. These jets, formed by the interaction of magnetic fields with hot gas, stretch across vast distances, often reaching thousands of light years into space. They are so energetic that they can even influence other galaxies far beyond Messier 87 itself, potentially altering their development. This phenomenon underscores the far-reaching impact of black holes on the larger cosmos. The very nature of a black hole presents a paradox. Its gravitational pull is so strong that once anything crosses its event horizon, the point beyond which nothing can escape, not even light can escape. This creates an environment where time and space behave in bizarre and extreme ways, distorting our understanding of the laws of physics. The forces at play near a black hole are so intense that they challenge everything we thought we knew about the universe. These strange and extreme conditions bring to light the paradox of creation and destruction. The energy emitted by a black hole can illuminate distant regions of space, but it can also obliterate matter entirely, turning it into nothingness. Messier 87's black hole thus becomes a symbol of the awe-inspiring and eerie power that exists within the universe. It encapsulates a striking mixture of incredible energy and an unsettling sense of danger, revealing the fundamental forces that shape the cosmos in ways that are both magnificent and terrifying. The image of a black hole, as captured by the Event Horizon Telescope, provides us with a profound new way of looking at the universe. It is a vivid reminder of the mysteries that lurk in the cosmos, phenomena that challenge our understanding of physics and the very fabric of reality. For the first time, when we glimpsed the image of a black hole, it felt like witnessing the shadow of something that defies the natural laws as we know them. This image forces us to confront questions about the nature of existence, challenging our comprehension of time, space, and even the idea of life and death in the universe. The sight evokes a sense of awe and fear, simultaneously reminding us of the vast limits of human knowledge and the unimaginable forces at work in the universe. Scientists and explorers alike grapple with the role black holes play in the life cycle of stars and the formation of galaxies. They are no longer seen as mere cosmic oddities, but as integral players in the grand ballet of the universe. These supermassive black holes influence the behavior of light, matter, and even the structure of galaxies. As such, they serve not just as passive objects of study, but as critical keys to unlocking the deeper mysteries of the cosmos, reshaping our understanding of the universe and our place within it. Moreover, the idea that there exist regions in the universe where the familiar laws of physics seem to fail ignites our imagination in profound ways. This concept doesn't really capture the curiosity of scientists, but also captivates artists, philosophers, and thinkers, leaving an indelible mark on how we perceive the universe. It infuses our understanding with a sense of awe, mystery, and even fear, urging us to ask deeper questions about the cosmos and the very nature of reality. The black hole, a mysterious and enigmatic object, stands as a symbol of the unknown, challenging us to question what lies beyond the limits of our current knowledge and encouraging future generations to venture into the far reaches of space. Such an image acts as a catalyst, compelling humanity to seek answers to fundamental questions surrounding gravity, time, and the essence of existence. The black hole does not merely exist as an abstract concept. It acts as an invitation for further exploration. It represents a riddle wrapped in darkness, one that beckons us to probe deeper into the unknown, even as we come to terms with our limited understanding. Through this search for knowledge, we are forced to confront the vastness and complexity of space itself. We find ourselves caught in a never-ending cycle of discovery and wonder, drawn ever further by the gravitational pull of the questions that black holes present. A particularly fascinating example lies in the black hole at the heart of NGC 4395, a spiral galaxy located approximately 14 million light-years away from Earth. This black hole challenges many of our traditional assumptions about galactic centers. For decades, scientists have adhered to the belief that supermassive black holes, vast and dense regions located at the centers of galaxies, must have brightly lit and energetic surroundings, filled with infalling gas, dust, and stars. These glowing accretion disks, the swirling mass of matter spiraling toward the event horizon of a black hole, serve as spectacular markers of immense gravitational forces at play. The intense radiation emitted by the heated material often becomes a beacon, visible across vast distances and hinting at the tumultuous processes unfolding within. However, NGC 4395 defies these expectations. Unlike its more active counterparts, this black hole is surprisingly dim and quiet. It's as though, in the midst of the cosmic storm that other black holes generate, NGC 4395 sits in an eerie, subdued silence. To grasp the significance of this, imagine visiting a bustling city center where every street is alive with light and activity. Now imagine discovering a quiet, almost deserted neighborhood tucked away on the outskirts, a place where little happens, where shadows seem to linger longer and the air feels still. that is analogous to what astronomers have found in NGC 4395. The faint nature of its black hole suggests it does not pull in matter at a rapid rate, resulting in a dimmer, less conspicuous appearance compared to other black holes. This surprising observation raises profound questions about the nature of black holes and their surrounding environments. It suggests that not all black holes may need to be active, consuming vast amounts of matter to survive or influence their galaxies. In fact, NGC 4395 implies that black holes can exist in a far more subdued state, perhaps quietly shaping their galaxies without the explosive, dramatic activity that typically characterizes these cosmic behemoths. It challenges our traditional understanding, encouraging us to consider that there are facets of the universe that don't fit neatly into our preconceived notions. This realization opens up a vast array of possibilities, prompting further exploration into how galaxies and their centers evolve over cosmic time. Even a small black hole, like the one in NGC 4395, can offer profound insights into the cosmic forces at play. Imagine black holes as vast cosmic vacuum cleaners. Even a relatively modest black hole can possess an extraordinarily strong gravitational pull, capable of drawing in nearby objects without warning. The more active a black hole becomes, the more material it consumes, creating a volatile and energetic environment. As matter spirals inward, it heats up to staggering temperatures and emits intense radiation, transforming the black hole into a beacon of light in an otherwise dark universe. This energetic display signals that even a small black hole can have a profound influence on its surroundings, triggering dramatic shifts in the fabric of space. But there is an even deeper layer of concern with black holes of this size. Their relatively subtle nature makes them harder to detect, and thus they may remain undetected for extended periods, quietly lurking in the background. This hidden presence raises alarm, for such black holes may be situated near other celestial bodies, potentially disrupting their orbits or causing gravitational anomalies. Without warning, they could change the trajectory of nearby stars or planets, as if a predator were waiting in the shadows, ready to pounce. This danger lurks within the cosmos, where the smallest black holes can have the largest consequences. The combination of size and inactivity may conceal a formidable threat, one that could wreak havoc on its environment, altering the delicate balance of the universe. In the case of NGC 4395, this dynamic is especially intriguing. Despite the black hole's lack of activity, it possesses the potential to alter its galactic environment in significant ways, casting ripples through space that we are only beginning to understand. The realization that even a small black hole could create profound changes in its surroundings forces us to reconsider how we think about these cosmic objects. No longer simply the destructive engines of chaos, black holes may also play a quieter, more subtle role in shaping the galaxies they inhabit. The more we learn about them, the more we are forced to acknowledge the unexpected complexity of the universe. At the heart of NGC 4395, the black hole becomes a gateway to understanding the fundamental dynamics of the universe. As researchers delve deeper into the nature of this mysterious object, they are not merely expanding our scientific knowledge, but also pushing the boundaries of human curiosity. This search for understanding is deeply philosophical, touching on some of humanity's oldest and most profound questions about existence and mortality. The black hole represents the ultimate enigma, where gravitational forces are so intense that nothing, not even light, can escape. It embodies the unknown, the cosmic forces that we can only begin to grasp, and through this exploration, we inch closer to understanding the hidden fabric of reality itself. Moreover, studying the interactions between the black hole and its galactic surroundings offers more than just answers to theoretical questions. It provides us with insight into cosmic events that may, in time, affect our own universe. As matter falls into the black hole, it is heated to extraordinary temperatures, emitting radiation that can be detected from across vast distances. This process, which we can observe from the safety of our planet, mirrors the cataclysmic events that we fear might one day impact Earth. In this way, black holes serve as a reminder that the universe is in constant motion, constantly shifting and evolving, and that we too are subject to the same forces that shape the cosmos. The star formation occurring in NGC 4395 further enhances the intrigue surrounding this galaxy. The interactions between the black hole and the gas and dust clouds of the galaxy provide a glimpse into the evolutionary processes of galaxies over time. As stars form and die, as gas is drawn toward the black hole, we are reminded of the fragile nature of our own existence in the grand scheme of the cosmos. The study of these processes forces us to confront our own vulnerability and the transience of our place within this ever-changing universe. Ultimately, the exploration of NGC 43395 and its black hole is as much a journey into our own psyche as it is a scientific pursuit. As we examine the deeper mysteries of the universe, we are forced to confront our own fears of the unknown, of the unimaginable forces that shape the fabric of reality. Yet, in this pursuit of knowledge, we also find inspiration and awe. The more we learn, the more we come to understand our place in the cosmos and the fragile nature of our existence. We are no longer passive observers of the universe, but active participants in the quest for answers, driven by curiosity and wonder. The black hole at the heart of NGC 1365, another spiral galaxy, offers a similarly intense look into the forces that govern the universe. Unlike the quiet black hole of NGC 4395, this black hole is surrounded by a luminous accretion disk, a swirling mass of gas and dust that is heated to extreme temperatures as it falls into the black hole's grasp. The energy released from this process emits powerful radiation, visible in the form of X-rays, radio waves, and even visible light. This glow cuts through the surrounding darkness, allowing astronomers to study the black hole from a distance and further unravel the mysteries of these cosmic giants. Through this study, we gain not only a deeper understanding of black holes, but also insight into the larger forces that shape the universe as a whole. Moreover, the immense gravitational pull exerted by a black hole can influence not just the space around it, but also the stars and gas clouds in its immediate vicinity. These interactions, though subtle at first glance, can cause stars to accelerate, generating powerful bursts of energy in the process. Observing these high-energy emissions provides invaluable evidence of the black hole's existence and its insatiable power. In order to capture this dynamic interaction, scientists rely on advanced telescopes, which are specially equipped to detect various wavelengths of light. Through these instruments, researchers are able to visualize the unseen, a process that allows the energy radiating from the black hole's surrounding material to become visible to the human eye. This radiant activity, though originating from the chaotic region near the black hole, is crucial in unveiling the true nature of these cosmic monsters. Black holes, as dark and enigmatic as they are, leave behind an unmistakable signature in the form of high-energy emissions from the surrounding material. The intense and unpredictable behavior of the matter surrounding the black hole reveals much about the forces at play and sheds light on the dramatic processes that occur in these extraordinary phenomena. It's a phenomenon that, when observed, evokes a sense of awe and mystery, turning the black hole from an invisible force into a glaring focal point of cosmic activity. In particular, a rapidly rotating black hole, often referred to as a curved black hole, possesses unique characteristics that amplify its already mysterious and, at times, terrifying nature. When a black hole spins, its rotation doesn't simply resemble the spinning of a planet or a star. It influences the very fabric of space itself. To better understand this, imagine placing your hand in a pool of water and stirring it. As you stir faster, the water creates swirling currents and whirlpools, pulling everything in its path. Similarly, the rotation of a black hole causes space to twist and bend around it in a manner that is nearly impossible to visualize. This twisting effect, known as frame dragging, means that anything entering the black hole's vicinity gets caught in this ever-tightening spiral. Objects that venture too close to the black hole experience extreme gravitational forces that pull them inward, distorting their shape and stretching them out to extraordinary lengths. This leads to a phenomenon often referred to as spaghettification. The black hole's rapid rotation amplifies the gravitational effects, creating an environment where the very laws of physics seem to break down. In this hostile environment, time itself stretches and warps, challenging everything we know about the universe. Moreover, the energy at the edges of a rapidly rotating black hole gives it the power to eject high-energy jets of particles, streams of matter that shoot outward at nearly the speed of light. These jets, which can be seen in distant galaxies, serve as an astonishing visual reminder of the black hole's relentless power. Despite its insatiable hunger for matter, a black hole is not simply a passive force that devours everything in its path. It also expels energy in violent, dramatic bursts, adding to the chaos of its surroundings. This interplay between energy absorption and ejection creates a sense of cosmic horror, transforming the black hole from a mere void into a destructive, almost sentient force of nature. The combination of intense gravitational pull, the distortion of space and time, and the violent ejections from the black hole creates a remarkable environment that challenges our understanding of the cosmos. These elements converge to shape an incredibly dynamic and chaotic system, one that is both awe-inspiring and terrifying. A black hole, especially one with rapid rotation, is not merely a region of darkness, but rather a center of unfathomable power and complexity, a maelstrom of destruction and intrigue that stretches our imagination to its limits. Consider the case of the galaxy NGC 1365, which houses a supermassive black hole at its core. This black hole plays a crucial role in shaping the environment surrounding it, and the relationship between the two is a fascinating, almost poetic dance. Picture a grand cosmic ballet where the black hole is the principal dancer, exerting immense gravitational forces on the stars around it. As these stars orbit the black hole, their movements follow paths shaped by its gravity. The closer a star gets to the black hole, the faster it must travel to avoid being pulled in. This delicate balance creates a dynamic interaction where the black hole's gravitational pull accelerates the stars to incredible speeds. Over time, the black hole and the stars exchange momentum in a manner similar to how billiard balls collide and bounce off one another. However, the influence of the black hole extends far beyond simply moving stars around. It also shapes the very structure and stability of the galaxy itself. The gravitational tides caused by the black hole can alter the orbits of countless stars, affecting their life cycles and even influencing star formation within NGC 1365. Areas of gas and dust near the black hole may become compressed, providing the necessary conditions for new stars to form. Conversely, stars that venture too close may be torn apart by the black hole's immense forces. This eerie and symbiotic connection between the black hole and the stars illustrates the intricate and interconnected nature of cosmic phenomena. It's a relationship where the black hole not only draws matter in, but also influences the very birth and death of stars. But the influence of these cosmic giants doesn't stop there. Stars, in turn, also contribute to the black hole's feeding process. As stars move in and out of the black hole's gravitational reach, they provide essential material that the black hole consumes, often leading to bursts of energy that can be observed as bright emissions across various wavelengths. This ongoing interplay creates a complex web of influence, where both the black hole and the stars impact each other, contributing to the dynamic evolution of the galaxy. In a similar vein, the binary black hole system of PG 1302-102 presents an equally captivating and unsettling chapter in our understanding of the universe. This system is home to two supermassive black holes that orbit one another at a blistering pace, their rapid motion raising profound questions about the nature of gravity, cosmic evolution, and the black holes themselves. As these two black holes spiral around each other, their gravitational attraction causes them to release gravitational waves, ripples in space-time that spread outwards, detectable even far from the source. This phenomenon not only confirms the predictions made by Einstein's theory of relativity, but also opens up an entirely new avenue of research, allowing us to better understand the behavior of these monstrous entities. However, the unsettling part of this discovery lies in the scale and power of these black holes. Located at the centers of galaxies, their interactions could date back billions of years, suggesting a long and tumultuous history. The gravitational waves emitted by these black holes offer a glimpse into the violent and ancient history of the cosmos. These interactions are not isolated events. They could have significant effects on their surrounding environments, influencing everything from star formation to the overall behavior of galaxies. The study of such systems helps illuminate the complex and often unpredictable nature of the universe, shedding light on the hidden forces that shape the very fabric of existence itself. The rapid motion of celestial bodies suggests a remarkable instability in their orbits, one that heightens the probability of a cosmic collision in the distant future. When two black holes inevitably collide, the resulting event releases an inconceivable amount of energy, momentarily eclipsing the brilliance of every star in the universe combined. Such cataclysmic occurrences stir profound questions regarding the very nature of space-time and the far-reaching consequences of the energy released on galactic scales. At the heart of this cosmic drama lies the binary black hole system PG 1302-102, which serves not only as an extraordinary case study in the field of astrophysics, but also as a stark reminder of the dynamic and violent forces that govern the universe. Its swift, almost frenetic motion beckons us to unravel the deeper mysteries surrounding black holes, the evolution of galaxies, and the fundamental laws of physics that underlie the vast expanse of everything we observe. Astronomers see the merging of black holes as an event that could unleash an almost unimaginable amount of energy, one that has the potential to revolutionize our understanding of the cosmos. Imagine for a moment two massive objects, each a black hole, swirling around one another in the cold emptiness of space. Their gravitational pull is so intense that nothing, not even light, can escape their grasp. As they orbit each other, their immense gravitational fields draw them closer, spiraling inward, relentlessly closing the gap between them. This is not a quick process. It takes time. Gradually, they lose energy through gravitational waves, ripples in the fabric of space-time that carry vital information about their movement, much like how sound waves travel through air. Eventually, when the two black holes collide, they merge into a larger black hole, releasing an unfathomable amount of energy, more than the combined output of all the stars in an entire galaxy. This cosmic cataclysm is not only awe-inspiring, but also profoundly exciting for astronomers, as it presents an opportunity to explore the fundamental laws of physics, particularly how gravity behaves under extreme conditions. Gravitational wave observatories have already detected signals from past black hole mergers, capturing the cosmic sound waves generated by these colossal events. Each signal detected provides astronomers with invaluable data, helping them piece together a clearer picture of the interactions between these enigmatic cosmic entities. As they continue to observe and analyze these celestial phenomena, astronomers are not merely anticipating the merger itself, but are also looking forward to the aftermath, which could reveal hidden truths about the very fabric of reality. Questions about dark matter, the nature of gravity, and even the origins of the universe itself are all potential discoveries that may be unlocked by the study of these cosmic explosions. In this sense, the merging of black holes is more than just a spectacular event in the distant reaches of space. It is a window into the deepest and most fundamental aspects of the universe, allowing us to probe the forces that govern the very structure of reality. The binary black hole system PG 1302-102, with its chaotic and extreme interactions, is a fascinating example of how the universe operates. At the core of this violent system lies a black hole, a region of space where gravity is so intense that it warps everything around it, exerting a tremendous force on any matter caught in its grasp. As stars spiral toward this invisible behemoth, they often collide in a cosmic dance of destruction, releasing massive amounts of energy, frequently in the form of brilliant bursts of radiation. The destruction of one star can, in certain cases, lead to the creation of new stars or even new planetary systems. But this process is not without its darker consequences. The energy released during these interactions can strip away the atmospheres of nearby planets, making them uninhabitable. The implications of such violent events raise chilling questions about the stability of life in the universe. How many potential worlds have been wiped out before they could even begin to develop? PG 132-102 therefore serves as a vivid reminder that while the universe is capable of creating beauty and complexity, it is also an arena where violence and destruction are fundamental forces. These interactions push us to reflect on our place in this vast, unpredictable expanse and to recognize that life as we know it exists only amid the remnants of countless cosmic battles, some of which are still unfolding. Another dramatic example of cosmic violence is the neutron star merger designated GW170817. This cataclysmic event provided significant insights into the formation of black holes. Picture a few neutron stars, each one so dense that it is almost entirely composed of neutrons, spinning around one another in an ever-tightening orbit. As they spiral closer and closer, their gravitational forces accelerate, and then, in a cataclysmic collision, they release an enormous amount of energy. Gravitational waves, ripples in space-time, are sent out across the universe, and the force of the collision tears the neutron stars apart, sending heavy elements like gold and platinum into space. This violent explosion lights up the cosmos, providing scientists with a fleeting but spectacular view of this cosmic catastrophe. But the true significance of this event lies in what happens next. As the neutron stars collide, the remaining core may be dense enough to collapse under its own gravity, surpassing a critical threshold. When this occurs, the core can transform into a black hole, a process that reveals just how violent and dramatic the formation of these enigmatic objects can be. The merger of these neutron stars demonstrates a process known as kilonova, a brilliant explosion that occurs when the debris ejected during the collision produces and spreads heavy elements throughout space. This contributes to the cosmic cycle of matter, enriching the universe with new elements that will, over time, form new stars, planets, and potentially life itself. GW170817 is not just a powerful display of the energy released during a neutron star collision. It also serves as a crucial piece of the puzzle that allows scientists to expand their understanding of black holes and the processes that lead to their formation. The event is a reminder of how violent the universe can be, but also of how such destruction leads to the creation of new worlds and new cosmic entities. At the heart of these observations is the phenomenon of gravitational waves, ripples in spacetime created by some of the most violent events in the cosmos. Imagine dropping a stone into a still pond. The waves spread outward, displacing the water. Gravitational waves operate in a similar way, but instead of traveling through water, they travel through the very fabric of space itself. When two massive objects, such as black holes or neutron stars, collide, they create ripples that propagate across the universe, stretching and squeezing space-time as they go. These waves carry valuable information about the source of the collision, the masses of the objects involved, the forces at play during the event, and the way they interact. By studying these gravitational waves, scientists are able to learn about the universe's most violent and energetic moments, revealing the drama and complexity of cosmic events that would otherwise remain hidden. Gravitational waves serve as the universe's messengers, telling us about the cataclysmic events happening throughout the cosmos. The detection of these waves opens up new realms of understanding about how the universe behaves on the grandest scales. Cosmic collisions, whether the merging of black holes, neutron stars, or even entire galaxies, reshape our perception of how celestial bodies interact. These collisions don't just result in the destruction of matter. They also give birth to new stars and planetary systems, showing us that in the vast, chaotic dance of the cosmos, destruction and creation are intimately intertwined. In this grand ballet of the universe, each cosmic collision is both an ending and a beginning, a violent but necessary force in the ongoing evolution of the universe. However, the consequences of cosmic collisions can be terrifying in their magnitude and complexity. These colossal events, involving immense forces and unimaginable energies, can sometimes lead to the formation of black holes or even trigger catastrophic supernova explosions. Supernovae, one of the universe's most violent phenomena, occur when massive stars exhaust their nuclear fuel and collapse in on themselves. The resulting explosions release energy on an extraordinary scale, shaking the surrounding space and reshaping entire star systems. These cosmic events, while destructive, also hold valuable clues for understanding the universe's structure and evolution. Through the study of such collisions, scientists gain deeper insights into the larger-scale architecture of the universe. For example, when two galaxies collide, The resulting aftermath provides a window into how galaxy clusters are formed and how they evolve over time. Observing the aftermath of these collisions reveals patterns that explain the distribution of dark matter, an invisible substance that plays a crucial role in the gravitational dynamics of galaxies. Dark matter shapes the way galaxies move and interact with one another, influencing their formation and the very evolution of cosmic structures. Moreover, understanding the intricacies of cosmic collisions goes beyond merely mapping the universe's structure. It also has far-reaching implications for the potential habitability of distant planets. As stars and planets collide or pass near one another, their gravitational interactions can dramatically alter their orbits. A planet's journey through space, influenced by these gravitational forces, can ultimately determine whether it remains in a habitable zone, where conditions might support life. The more we learn about these chaotic events, the clearer our understanding of the delicate balance required for life to emerge becomes. The study of cosmic collisions, therefore, does more than simply illuminate the past of our universe. It also offers a glimpse into its future. These events teach us that although the universe operates on a foundation of chaos, that very chaos can lead to creation. New stars are born from the ashes of supernovae, and galaxies are formed from the remnants of their interactions. The universe is a constantly evolving entity, with forces at work that we are just beginning to comprehend fully. A prime example of the fascinating interplay between cosmic objects is the millisecond pulsar J1748-2446 AD. This extraordinary object resides deep within the heart of our galaxy, where extreme conditions and massive gravitational forces create a unique environment. A pulsar, a rapidly spinning neutron star, emits regular beams of radiation, akin to a lighthouse flashing across space. J1748-2446 AD, spinning at an astonishing speed, completes a full rotation dozens of times each second. As it spins, it sends out pulses that can be detected across vast distances, providing us with a glimpse into the most extreme physical conditions in the universe. What makes this pulsar especially intriguing is its proximity to a black hole. Their relationship is dramatic, filled with intense gravitational interactions. The pulsar's rotating magnetic field exerts a pull on the material surrounding it, drawing in gas and matter from its nearby companion star. As this material spirals inward, it forms an accretion disk around the pulsar, creating a high-energy zone of bright X-ray emissions. This process, while fascinating in its own right, is made even more dramatic by the presence of the black hole lurking just nearby. The black hole's influence is subtle but powerful. It acts like a silent predator, quietly feeding on the material drawn toward it, while the pulsar continues to emit its regular pulses of radiation. The interaction between the pulsar and the black hole causes complex gravitational dynamics, influencing the behavior of both objects in unexpected ways. The pulsar remains a vibrant beacon of energy, its regular pulses shining brightly, while the black hole quietly exerts its gravitational pull, slowly but surely affecting the entire environment. J1748-2446 AD represents a perfect example of the cosmic dance that occurs between pulsars and black holes. While the pulsar beams out its radiation, it also exists in a constant battle for survival, its fate intricately linked to the presence of the unseen black hole. This relationship serves as a reminder that in the vast, mysterious reaches of space, even the most stable and seemingly harmless objects are subject to the ever-present threat of more powerful forces. This cosmic interaction offers valuable insights into the behavior of black holes and their profound effect on the material around them. Pulsars, like J1748-2446 AD, are not only fascinating because of their regular emission of radiation, but also because their interactions with nearby matter, be it gas, dust, or even other stars, can generate shock waves and compression in the surrounding space. These shock waves can, in turn, affect the behavior of nearby objects. This dynamic is mirrored in the way black holes influence their surroundings. Black holes exert powerful gravitational forces, drawing in gas and dust and heating them to extreme temperatures, often emitting intense radiation in the process. The material around black holes becomes part of a swirling disk, pulled in by the black hole's gravitational field, eventually spiraling inward. This process, while dangerous, also plays a key role in shaping the surrounding environment. The radiation emitted during this process can influence star formation, the evolution of galaxies, and the very structure of the cosmos. Thus, the study of pulsars like J 748 2446 AD helps us understand not only the behaviors of individual stars, but also the broader cosmic forces at work in the universe. Black holes, like pulsars, are instrumental in shaping the universe as we know it. J 748 2446 AD offers an extraordinary opportunity for scientists to explore the extreme physical conditions that govern neutron stars and black holes. Its rapid rotation and interaction with nearby material provide researchers with the chance to study the behavior of matter under the most intense gravitational forces. These interactions can reveal much about how matter behaves under extreme conditions, offering insights that help explain the behaviors of more mysterious and exotic objects in the universe. Moreover, the study of pulsars like J 1748 2446 AD may also lead to the detection of gravitational waves, tiny ripples in spacetime that are generated by the most cataclysmic events in the cosmos, such as the collision of black holes or neutron stars. If a connection can be made between J 748 2446 AD and gravitational waves, it could revolutionize our understanding of the universe's most chaotic and violent events. Gravitational wave detection could provide a new way to observe the cosmos, allowing scientists to detect and study cosmic phenomena that are otherwise invisible to traditional telescopes. As we delve deeper into the mysteries of pulsars like J 1748 2446 AD, we might also confront unsettling questions about the future of our own star system. The delicate balance of forces that governs these cosmic interactions serves as a reminder of the fragile nature of the universe. Every new discovery highlights the unpredictable nature of the cosmos and the immense forces at play. Each revelation about pulsars, black holes, and other cosmic phenomena brings us closer to understanding the complex forces that shape the universe and, by extension, our place within it. Similarly, black hole XTJ 118 plus 480 has captivated scientists with its fascinating behavior. Located about 6,000 light-years from Earth, XTJ 118 plus 480 is part of a binary system paired with a companion star. As the black hole interacts with its partner, it pulls material from the star toward itself, creating a swirling disk of gas and dust. This disk heats up as it spirals inward, generating bright X-rays that make XTJ 118 plus 480 one of the most luminous black holes in our vicinity. What makes this black hole particularly interesting is its proximity to Earth. Being relatively close allows astronomers to study its behavior and the effects it has on its surrounding environment in ways that are not possible with more distant black holes. Observations reveal that XTJ 180 plus 480 is moving through the galaxy at high speeds, suggesting it may have originated from a dense star cluster before being flung out into its current orbit. This motion provides valuable insights into the chaotic and violent history of star formation and interactions in our galaxy. By studying XTJ 108 plus 480, scientists are learning more about the dynamic and often unpredictable nature of black holes. These cosmic giants are not stationary objects, but are instead part of an ongoing cosmic journey. As they move through the galaxy, they shape their environments in profound ways, influencing the stars, gas, and matter around them. Each new discovery adds another layer to our understanding of these enigmatic objects and the complex forces at work in the universe. The black hole's behavior offers profound insights into the way it accumulates mass as it draws in surrounding matter. This process not only illuminates the intricate mechanics of black holes, but also highlights the complex relationship between these cosmic giants and the stars they interact with. As the black hole feeds, it emphasizes the dynamic nature of stellar evolution, particularly the fate of stars that find themselves in close proximity to these gravitational behemoths. Such interactions offer a key to understanding how stars evolve and eventually meet their end in the unforgiving grasp of a black hole's influence. One of the most fascinating objects in this field of study is the cosmic entity known as XTJ 1118 plus 480. Located approximately 6,000 light-years away from Earth, this black hole acts as a unique laboratory, providing researchers with a rare opportunity to observe the life cycle of black holes. Through its actions, we learn about how black holes influence their environments and their role in the broader cosmic framework. XTJ 1118 plus 480's erratic movements through the galaxy create ripples that extend far beyond its immediate vicinity, offering a glimpse into the ever-shifting nature of the universe itself. This particular black hole has provided astronomers with a captivating puzzle. Traditionally, black holes are thought to reside within the centers of galaxies or specific stellar systems. However, the discovery of rogue black holes that have been ejected from their original locations and now drift freely through the cosmos, challenges our preconceived notions about the boundaries of space. These rogue black holes, which wander through the universe independent of any star system, force us to reconsider the sense of cosmic safety. While black holes are indeed massive and possess powerful gravitational forces, their effects are not typically felt until one ventures too close, entering the region known as the event horizon. The idea of rogue black holes upends long-held assumptions about the stability of the galaxy. Our Milky Way, once perceived as a relatively safe and bounded environment, now seems more precarious, with the potential for encounters with these wandering giants. A rogue black hole could pass through any region of space, even dense star clusters, where its gravitational pull could disrupt the orbits of nearby stars, initiating a cascade of cosmic events. This introduces a new layer of unpredictability and danger in the vastness of the galaxy. The wandering nature of rogue black holes raises important questions. How do these nomadic giants influence their surroundings? How do they interact with the environments they pass through? And what impact might they have on the formation and evolution of galaxies? The origins of rogue black holes are varied and often tied to the cataclysmic aftermath of stellar events. Some may be the result of star collisions or mergers, while others may date back to the early moments of the universe, formed under primordial conditions. Unlike their more stationary counterparts, rogue black holes cannot be easily studied or tracked. Their unpredictable trajectories make them difficult to study, leaving scientists with more questions than answers. They may pass through regions of high-density material, feeding on whatever they encounter, which could alter the dynamics of entire star systems. This makes the study of rogue black holes a challenge and a puzzle that astronomers are eager to solve. The unpredictability of these wandering black holes forces us to rethink the cosmic order. They are not just passive observers in the galaxy, but active participants that influence the environment around them. These rogue black holes, acting as cosmic nomads, may play a crucial role in shaping the galaxies they traverse. Their movements could stir the creation of new stars or cause the destruction of existing ones. As they drift through the galaxy, they could even affect the evolution of entire solar systems, feeding on material and altering the course of cosmic history. XTJ 1118 plus 480 stands out not only because of its wandering nature, but also due to its intense and erratic behavior. It is a stellar black hole formed from the remnants of a massive star that has exhausted its nuclear fuel. As it journeys through the galaxy, its path is far from predictable. This black hole exhibits erratic movements, emitting bursts of energy that suggest it is far from ordinary. These sudden flares of radiation hint at the complex interactions occurring within and around the black hole. By studying these emissions, scientists are given a rare glimpse into the inner workings of black holes and how they interact with nearby stars. This unique behavior is not just a curiosity, it serves as a key to understanding the broader questions of physics. How do black holes influence the stars they interact with? How does the presence of a black hole alter the behavior of matter under extreme gravitational forces? These are fundamental questions that XTJ 1118 plus 480 may help answer. The way this black hole pulls material from a companion star, emits powerful jets of radiation, and moves erratically provides valuable data that could potentially change our understanding of the laws of physics. The study of XTJ 1118 plus 480 also opens the door to deeper questions about the nature of black holes themselves. Are there different types of behaviors exhibited by black holes, or do they all follow a similar pattern? How do these cosmic giants influence their surroundings on a larger scale? Investigating the behavior of XTJ 1118 plus 480 may lead to the discovery of new aspects of the universe that are not yet understood. It serves as a living laboratory for researchers, providing clues to the complex relationships between gravity, high-energy processes, and the forces that govern the cosmos. Ultimately, the presence and behavior of XTJ 1 to 118 plus 480 reveal the intricate tapestry of the universe, woven together by the interactions of massive celestial bodies. These cosmic forces shape the galaxy, sometimes in predictable ways, but often with an unpredictability that makes the universe both beautiful and dangerous. The discovery of rogue black holes, coupled with the study of objects like XTJ 1118 plus 480, forces us to confront the complexities of the universe. The galaxy is not the safe, predictable environment we once believed it to be, but a dynamic and sometimes chaotic arena where the laws of physics and the movements of celestial bodies can create stunning and sometimes perilous outcomes.